Hello everyone, welcome to this course. It's gonna be a wild ride, really exciting things coming up, and we will check so many concepts, algorithms, models, architectures. We'll dive into history, we will do some really fun projects. In the first week, you're gonna dive into the very basic concept about your roadmap into AI development. We will check a bunch of math theory. Math is one of the main recipes for AI, for machine learning. It will be the flour in the bakery business. It's a core fundamental to do everything. We will obviously just check the basics. There's not like all the time in the world to check every single concept, but the main algorithms, the main basic features, and the main basic development about linear algebra will be essential. We will also check lots of different concepts about AI itself, a little bit of history, a little bit about theory, and we will dive into a refresher about Python first. I know not everyone has the same level of knowledge in terms of technical skills, so we will check a little bit about computer architecture too. We're gonna start with the Python refresher, talking about my setup I have here, different kind of OS, different kind of needs and requirements you will need throughout this course. Not everything is a must-have, you can opt for many different solutions and we will check everything as we go. These are really exciting times, technology is advancing a lot. And the way the AI field is moving in a daily basis is really incredible. All of these things we will see throughout this course will help you understand how to develop your own architectures, what's happening when a nuance and a new discovery happens in AI, all the new implementations based on all architectures and everything. So a really excited time, can't wait to start all of this and guide you into this journey. You can apply all this knowledge into every field you can possibly choose. If you plan to stay in a VFX career or game development, even if you change that completely, if you want to be a lawyer, work in finances, all this knowledge will apply into any single field or career path you want to choose. Hello and welcome to this. It's going to be a really exciting course. We're going to check so many things. The first week and at the beginning of each week will be mainly theory, but we will go hands-on and apply lots of things. We will use lots of cool different tools for visualization and make sure we really understand the next steps. There's a lot in AI. Obviously, it will take forever to check every single thing, but I will guide you into the proper path so you can go deeper in your own time. So let's start checking this. The first thing we're going to check is theory itself about the kind of development we're going to do, and the main concept about this whole new world, new quote-unquote, of technology. Now, AI has been used for a long time. It is a misconception that people think is a new thing, but it's not. We're using really old algorithms, and indeed, there's new nuances when different companies and developers and different people are coming on with new frameworks, new architectures, and it's really exciting to check everything. We want to start with this familiar concept about what is artificial intelligence. A lot of people get confused in these terminologies and they use it interchangeably without noticing that they are different things but maybe in the same field. So let's start getting familiar with these kind of approaches and these structures we have here. Artificial intelligence is the main concept, is the main field. As you can see here, we are surrounding and we are inside this field when we're talking about machine learning, neural networks, and deep learning. Artificial intelligence is the main concept. Machine learning is a subfield of artificial intelligence. Neural networks are a subfield of machine learning. Neural networks are composed by deep learning or deep learning architectures. So we will see about all of this, and we really need to get familiar with the first steps first. In the field of AI, artificial intelligence refers as the ability for a machine to create tasks similar to a human, or to understand something in a way a human will do. That's the overall broad concept. That's the first layer of abstraction we're gonna use. So some common fields in artificial intelligence will be, for example, NLP, which you are using nowadays a lot. That's natural language processing. We also have visual perception, how a machine can visualize things and understand it, similar to a way to a human can do that. We have intelligent robotics, we have automated programming, we have knowledge representation, expert systems, planning and scheduling, speech recognition, problem solving and search strategies, and many, many more fields. So if you think about just one quick example, some robot developed in the 80s, it's not going to be the same framework and technology and architectures we use nowadays with deep neural networks, for example. It's maybe some basic algorithm to identify patterns and things, but we're building on top over time. And we will see in the next videos some exercise starting from a primitive way of solving something which is still considered AI. We will see about some of these main topics in artificial intelligence, but mainly throughout this course, we're gonna be in the blue, orange, and this dark pink section down here. So it will be mainly machine learning, neural networks, and deep learning. This is an introduction. You really need to be familiar with all these concepts and different architectures and knowledge so you can start applying something. Let me draw a quick diagram for you. If you're familiar with my courses in the past, or my methodology will be the following. If you are someone in a company and you're just an employee and you're working for the company, you're not gonna be a great value as an employee and in your career if you're just a user, just a basic user. What I mean by that is you're just in some location in your main company and you just represent a tiny part of this whole company. And if you just sit down there using tools, you're just a user. If you don't have a tool or some kind of program or something that will allow you to do task A or task B, you are waiting there until people create these tools for you. You see? Now, if you have other people with technical knowledge and these people are creating these tools, they immediately have a bigger chunk quality-wise in a company. So these are the people, let's call it D for developers, creating these tools, doing different architectures, doing different research and working. These developers are more valuable in a company. So if you want to step into this position, and maybe even more and more and more, the more technical knowledge you will need to know. In order to have more technical knowledge, you need to grasp some of these concepts and more in a lower level. For example, if you're just a user and your company is using AI and you're just using, for example, some tools to do deepfakes, or you have some other tools to do computer vision, maybe you have other tools to do automatic texturing, many different kinds of tools, not just AI tools, you're still just a user. This is not necessarily bad. You can do lots of things by just being a user, but career-wise, and the way technology advances, every time you are smaller and smaller if you're just some person using tools developed by someone else. Because if you're a developer, you can create a better version of these tools. You can create your own versions. That way, you're not using something done by someone else. You have full control in here. And now your company owns these tools. You're an integral part for this development, and you're a key structure in the bottom base of the company. Without you, the whole company falls apart. That way you're increasing value for yourself, for your career. Just keep that in mind. And this is the mindset we're gonna get. Every time we check something, we're gonna go as low level as possible to make sure we're understanding something. I've seen some cases of some people in some companies, for example in the VFX company, just using deepfake tools. But what if that deepfake tool is not behaving the way you want, you don't have good results, and so on? If you're the one creating that architecture, you will know how to tackle that issue, while this person is just waiting. I hope that's clear. I hope you understand why you need to have technical knowledge in the tool sets and architectures you are creating, you are developing. So with that in mind, we're gonna jump into the main concepts we will see, and we will do a roadmap of the kind of tools we're gonna be seeing all the way into this course. But just for now, keep in mind, AI, artificial intelligence, is the main field. Machine learning is a subfield of AI. Neural networks are a part or a subfield of machine learning, and deep learning is a subfield or a part of neural networks. And it works in that hierarchy. So the first things we're gonna check is just a quick overview on the kind of IDEs, on the kind of setups, hardware, software, and everything we're gonna be using in this course. And then we're gonna jump into different concepts for each one of these fields. When I get familiar with IPython, we're gonna be using notebooks a lot. And we need to start this with the very basic core for this. And that will be two things. One is linear algebra, the other one will be Python. We're gonna start with this. It will be the core for us to be familiar with. Obviously, I'm assuming you already know Python, but we're gonna do a quick overview on some kind of functionality and OOP. And we will have a quick overview as well about linear algebra and some of the core mathematical operations we will do in AI development. We're gonna move after that into some theory about these fields here and some of the concepts we will be seeing throughout this course. It will check a little bit on data science. Data science is intrinsic to machine learning. You can't do anything without data. So we will check some libraries, some way of plotting data and getting familiar with the data so you become one with your data. And then we will do and check some efficient ways of using your data. After all of that, you're gonna jump straight into machine learning and keep going from here to here. So now that we have that quick intro, let's talk a little bit more and dive a little bit deeper into this concept. As we know now, artificial intelligence will be the main field, and we have subfields as we more advance in technology. If we go back in time, for example in the 80s or 90s, when we have all sorts of AI, it can be the AI in a video game, a really primitive video game, but the AI is interacting with you. So it's like a fighting game where the other NPC is fighting with your character. It has some reaction and it has some actions to what's happening in the scene. Even when old school games like Doom, all of that behavior all the way back, including Pac-Man, will be still AI. But as you see, as you advance through time, we're still talking about artificial intelligence. We're just using new technology, new hardware, developing new algorithms, checking old algorithms, checking efficiency, new chips, new technology. It's all part of the same field, and many exciting stuff is being developed in parallel by many different smart people. So just in AI itself, in artificial intelligence, again, to be clear, this will refer as machines trying to understand things in a similar way that a human will do. If you're talking about visual perception, for example, if a human understands visually when he's seeing a particular animal or any kind of sign, a machine will do the same and try to identify those patterns and so on. If you're talking about the field of NLP, which you're using a lot nowadays, this field is natural language processing, anything to do with text. We also have expert systems, speech recognition, and so many more. I just have some examples here, but they are not the only ones. There are so many things just in AI itself. If you keep going deeper into machine learning, if artificial intelligence is the broad term, the broad field, and where a machine can understand things similar to a human, machine learning mainly refers to as the tasks itself. This is inside the field of AI, but in this time, we are treating this as a subfield because these will be tasks that are pretty much impossible for a human to do, but still in the same way of understanding things or trying to develop some things in some particular criteria. To give you one example, a human maybe can identify and split some documents. Maybe you have some documents for task A, or maybe you have some documents for task B, and so on. But imagine if you have like 10 million documents for task A and another 10 million for task B, and you need to separate them. Maybe a human can do that, but it will take like years for a human to do that visually, while a machine can do that in seconds. So every task that's pretty much impossible for a human, that's when we enter the field of machine learning. And I have some examples here. They are mixed, but we can split this in models and algorithms. So to give you another example, for models, we can have classifier models. And these models will use algorithms for classification. If you're talking about just classification, there are so many in here, like k-means, clustering, k-nearest neighbors, decision trees are used a lot in gaming, and so on. Many more examples and so many more things just in machine learning. If we start going deeper, this is basically like a time machine. If we start from an early adoption of AI, going into machine learning, now we're going into the future the deeper we go, because neural networks are not a new thing, but the way it's being developed nowadays with new technologies and with new frameworks is becoming the standard for everything. We will see really deeply about neural networks, but again, we will have layers and algorithms. For example, multi-layer perceptrons. A perceptron will be like one neuron. We will see that once we reach there. And you can use this for self-organizing maps, RNNs, autoencoders, modular neural networks, and so many more. Once we start going deeper into deep learning, it's basically a technology, it's an architecture that's going to use many layers of neural networks. The more we use it, the heavier the task will become. But there's so many in the field of deep learning, for example, convolutional neural networks, recurrent neural networks, generative AI, all the text processing, deep reinforcement learning, deep autoencoders, and again, so many more. Now, if we take a step back in time, like a decade ago, the way all these fields you see here and algorithms and everything were kind of their own island of research and development. If you see scientific papers and publications from like a decade ago, you will see like if you're trying to do some kind of AI in text processing, it's going to be its own thing with its own architectures and libraries and so on. If you're trying to work with images, it's going to be a different thing. And it's going to change again if you're trying to work with audio and so on. They were really different back then. But as everything progresses and we keep advancing through time, new discoveries happen all the time, pretty much on a weekly basis. And the one that took the industry by storm, the one that really changed the field of AI, is when the new architecture was introduced called transformers. And don't worry about this graph, you will get really familiar with this once we reach there. But basically nowadays, this is the main core architecture for everything. The way this was discovered, I think it was some doctors trying to do some translation of text. They came out with this new architecture. They didn't know, but this took the entire world of AI by storm and completely changed everything, because this architecture is so efficient if you compare with the old ones that nowadays pretty much everything is copy-paste of this as a base core of every architecture. It doesn't matter if you're dealing with text, images, audio, whatever you want. This is the transformer architecture, which is the core for everything. But the reason we're checking all of this in the right side, like going back in time into the past, first of all, is so you can understand where everything is coming from. And you can't do one without the other, because even when this is a new architecture, the transformer, it was built on top of all the other algorithms. Just some years ago, we were just using RNNs for text processing and LSTMs as well. Transformers are building on top of that, and just to give you one example, an autoencoder is an architecture of a transformer as well. So all of this, we'll get really familiar with every single thing in here, and we will check as we go what kind of model we can use, what kind of architecture we need to use. To give you another example, it can be very costly and extremely demanding and complex to create a super complicated AI model with lots of neurons, lots of deep learning layers, and many things in there. Not just costly because it's really heavy to train and maintain and deploy, obviously. The architecture itself of development can be extremely complex. And there was a case, a company was doing a document classification, and instead of training a heavy model, doing all sorts of fancy new algorithms, they just use k-means clustering, and is extremely cheaper than using something with super big neural networks and layers. And it proved better and cheaper and more efficient for the production to use those kind of models. Even when this is considered old, quote unquote, it's still used in a daily basis. I use it a lot. And you probably see this all the time when you're using all sorts of different programs. Again, to give you another example, if you're trying to classify, for example, the pixel values of color in an image, you can do that with k-means clustering as well, instead of training a super heavy model and doing something really complex and maybe unnecessary time, budget, computation, and you're just wasting resources. So you need to choose which one you're going to use, and we will see the benefits of choosing one or the other, and how we can maybe ensemble more, explore different versions, because for us, for AI developers, experiment is the main thing we do on a daily basis. You will do so many experiments with so many architectures, and you will compare everything all the time. Hello. So let's start checking some of the tools we will be using through this course. Some of these are optional, and it's not like absolutely necessary for you to have all of this. It's just the way I work, and some of later tools you will have to install them. Let's start by using and checking the OS itself. I'm using a Mac, I do this for all of the data manipulation, basically everything before training models and things like that. But for you, it will depend on the OS and your needs. We're gonna split this in two different ways. Let's just talk about Python. Let's forget about all the different kind of frameworks and different libraries and different stuff. Python itself, you're gonna be using it in two ways: default Python and IPython. IPython is basically interactive Python, because we will do lots of different things in a cell-based execution. So the main tools I use for default Python will be my editor is NeoVim, and even I have Vim emulators in different IDEs. And I also have tmux for the terminal itself, so I can switch in between sessions inside every terminal. These are my main tools as a developer, NeoVim and tmux. Regardless of the libraries and different things, we're gonna see one by one as we go. And for interactive Python, we will see a in-depth tutorial in the next video. For now, it's just a quick overview on the tools I have in my system, and it will be recommended for you to install some of these. Again, you don't have to use NeoVim as your editor. You can use whatever editor you want. And you don't have to have tmux if you don't use the terminal a lot. These are just conveniences for me, and I'm just explaining you a quick overview for these tools. So NeoVim and tmux, optional. Now let's check the tools that we actually gonna use in the course, and you need to install them. First of all, you're gonna be dealing with different Python environments. So for that, we're gonna be using Anaconda. So just go ahead and install Anaconda in your system, and then you will have access to create and set different experiments for different Python environments. We're gonna be using this a lot. You can go this in two ways. Anaconda itself is the big suite. It will come with lots of different applications. Now, in my day-to-day basis, I do use a lot of this, so I install Anaconda. Maybe you don't need all of this stuff. It can be really heavy. If you just want the functionality to create and manage Python environments, you can opt for Miniconda. So if you just Google Miniconda, it's a version of Anaconda with just the core functionality. It will be the same at the end. So this one doesn't come with lots of different packages, and Anaconda will come with lots of different packages, including Jupyer Notebook. If you just go for Miniconda, you have to manually install Jupyer Notebook. So we will see again about Jupyter in the next video. But also, if you don't have Jupyter installed in your machine, you're gonna be using Google Colab as well. This is the page for Jupyter. You can check some of the documentation, but this is Google Colab. Lots of different companies uses a framework like this. So it's a Jupyter-like based tools. Colab is this tool developed by Google and is a Jupyter-like quote-unquote IDE running in a web server, which will give you a GPU for free. And there are some pros and cons of using Colab, and we will see that as we go. But again, this is just a quick overview for this. Since we have a free GPU and allocation, these machines are not usually that powerful, and you can time out really fast as you're developing. Sometimes people choose to do local power, to use your own GPU and stuff like that. For that, we will use the native Jupyter Notebook from Anaconda, or if you manually install it, using your machine resources. So it's up to you. If you want to run everything in the cloud like Colab, or if you want to use your own local power, you can do that as well. And we will use it both. We will use cloud services and we will use local resources from your machine. In order to check some of that, let's take a look at some other tools I have here in this machine to do this kind of connections. So my terminal will be my main stage. If I'm doing basic Python or launching Jupyter Notebooks, it will be all from the terminal. So some of the tools I have here, obviously again, is tmux and NeoVim and stuff like that. So on the left side here, this is my local computer. This is my Mac, and I can start doing data manipulation. I can start checking some algorithms, some basic development, and all the stuff I need to do in here. But if I want to use a GPU, some CUDA development for later, I will also be connecting to another machine I have around the house. And I will do that via SSH. So if you have never used SSH before, just Google SSH. I can't really show you how to configure that because it's very OS dependent. So I don't know if you're using Linux, Mac, Windows, and I don't know which kind of connection you have, but it's very simple. In this case, my Linux machine already has SSH installed and is running. And the same here, I have my Mac SSH installed and I can connect to my Linux machine. And I do that all the time. This is just one example. I do exactly the same with the machines I have from work. I do the same to connect to different kind of companies. Obviously, there's other security measurements depending on the company. And it can be really tricky sometimes if you have like a super open connection, but let's not worry about that. This is at home. I'm just connecting to another computer with a GPU. So I have an alias to connect to my external machine. So right now, on the right side here, I am on my Linux machine, and I can prove it to you. Obviously, you can see here it's a different name and server than my Mac. And let's check the GPU. And I do have a GPU. It's a 3080, 16 gigs of VRAM. And now I have my resources. So if I need to use GPU and local power for my other machine, I'm connected to that machine here already. So we will use it like this sometimes. Sometimes we're gonna use cloud services. Sometimes we're gonna use your own machine. And sometimes you need to connect to an extra machine to have some power. Lots of different things we're gonna be doing will require CUDA or GPU architectures. So that's why we're gonna use this kind of connections, so we can use Linux machine. Or if you have a Windows machine already set up for you, you don't have to SSH to an external machine. If you're doing everything in just one machine, that's gonna work as well. I'm showing you the way I work because in this Mac particularly, this is kind of the logic I have on a day-to-day basis. I can work from home, from a coffee shop. I go to the office, I can go to different companies, and I just connect to the computers I need to do all the power. So those are some of the tools, and we'll probably check many more as we go. But in terms of IDEs and all of that, we're gonna mainly be using Jupyter Notebook. You can also use VS Code, and with VS Code, you can connect to different Python environments. I'll show you in a second how to deal with different environments. In VS Code, you can also create IPython notebooks. So some name and extension will be IPythonV for IPython notebook. Now we are in a Jupyter-like stage. We are in an IPython notebook. So notebooks are the main tool we're gonna be using throughout this course. And you can even choose the kernel and set the Conda environments you have in your machine. You can see all my environments in here for different experiments. I do have a Vim emulator here, so I'm ready to go with VS Code. And just for now, it will be necessary to have Docker installed. We will see about Docker way later. But just to be aware, we're gonna be dealing with containers, so we can keep stuff a little bit OS agnostic. Just have these tools installed if you want. For now, but we will check them one by one as we go. VS Code is optional again, because mainly we're gonna be using Jupyter, but we will jump here from time to time to check some things and some different kind of explorations in between notebooks and some common things we can have with all the cloud services and our local notebooks. So if you go back here again, it doesn't matter for me, either Linux or Mac. Let's check on this Linux machine. I have my Python environments in both. If you see here base, this is basically telling me that Anaconda is already properly installed. If I go here into my Mac, we also have base. Base is the default Python environment. Once you have Anaconda installed, you will have access to different Python environments, and you can create your own. And we will do that a lot of times. One of the first commands you can check is conda info --envs. It will list all the different virtual environments, Python environments you have in your machine. If you want to create a new one, and you will see this when we're checking repos and different scientific applications and stuff like that, lots of different experiments from different people or studios or even just single freelance developers. There are so many people doing lots of developments in AI. Many experiments will require very specific versions of some tools. That's why you want to have different virtual environments. We will check more in depth about Python environments later. For now, this is just a quick review on Anaconda itself. The way you can create a new environment is with the command conda create -n for name, and then you're gonna name it the name of your new Python environment. Let's just call it test. And then you need to assign a Python version. So you can do double equals or just equals. And let's say we are reading a paper and they use 3.10 or maybe 3.8 or 3.12. Whatever is the version, we're gonna install it like this. It's not locked forever, you can change it later, but this is a basic way of creating an environment. So if I hit enter, this will go ahead and ask you if you want to install that. It will come with lots of tools by default, and you want all of this like pip and so on. You hit enter, and then you have your environment created, but it's not yet. If you check the terminal, I'm still in the base environment, in the default one. In order to jump into the newly created environment, it will tell you the instructions here. You basically need to type conda activate and the name of the environment. Now you see in my terminal, I'm inside test because I name it like that. If you want to check the list of the packages you have in this environment, this is like your own isolated computer. Now you can do whatever experiment in here without messing up your OS. And if something fails catastrophically or you need to change it, you can always delete the entire environment. I'll show you that in a second, or change the versions. If you do pip list, this will be the list. Obviously comes with just the basic ones, and you can keep installing different packages here. For example, we need NumPy. Pip install NumPy. It will go into the server, it will connect the wheel, and it will install the package you want. Now if we do pip list again, you can see now we have NumPy. So that's how we're going to install different libraries. And you can always choose the version you want in here. For example, again, in some paper, they have a very specific version like 1.04 or something. You can always hard code the version you want in here. That's why we can create different Python environments. So we can check different versions of libraries, different technologies, and so on. So get used to this because we're going to use it a lot. We are inside this environment. We can jump out of this environment if we deactivate this. So conda deactivate. And now we are in base again. If you see here, conda info environment, you can see we have test in there, the one we just created. If you want to delete one of these, all you have to do is conda remove -n for the name of the environment and --all. It's gonna tell you, are you sure? Yes. So if we run conda info environments, we don't have test anymore. So you can jump inside environments, you can jump outside, and this is a great way of tracking different development. Just give it descriptive names, and then later we will have the same logic and do some containers so we can ship our models. This is the basic intro of some of the tools you're gonna use. We will check every single one of these in depth as we traverse through the course. Okay, let's talk about hardware. The kind of hardware you need, it will depend on your needs, but basically deploying into production, dealing with lots of data and big models, you will never be able to do that in a local machine. That's why we use data centers, that's why we use lots and lots of power. Same thing as if you're rendering a full movie. Potentially you can do it in your home machine, but it will take forever. You will run out of resources eventually. In the field of AI, the way we work, we start with small-scale experiments. Once we're drilling and tweaking some values and lots of different features, then we can escalate the model more and more and more. So we usually start with small experiments, but most of the stuff we're gonna be doing later will be GPU based. So if you still wanna use your own machine, or if you still wanna build your home machine for AI, you can search online, but basically processor, RAM, and a big GPU is what you need. I will say there's some articles like this one where you can check which best parts you can use, but to start with small experiments, I will say at least a 12 gigs VRAM GPU will be necessary. 8 will work as well, 8 gigabytes, but you will be very, very limited by doing that. I used to have lots of different computers in the house. I've been building computers since I was like probably 8 years old. Lately, for the past years, I completely got rid of everything and I'm just using laptops. Because the way I work with different companies, the models are so big, the development and deployment we do is so insane. Even if I had like 17 of these GPUs in a server in my house, it wouldn't be enough. So my way of working now is completely different. And the way you will work in a company will be different as well. If you think about VFX, for example, if you're rendering a movie, a shot for your movie, you're probably not using your own local power to do that. You are sending it into a farm, into a server to perform the job. So it's exactly the same thing. If you're working in AI in a company, you will never be using your own machine, your local power. You can manipulate data and do some algorithms in there, yes, but the main heavy load, the training and deploying, all of that will be done in cloud servers. So you need to get familiar with cloud services as well, and we will as we go with this. Just to keep in mind, you can also still use, again, your local power for small experiments, but once we start going bigger, you will need to switch to a cloud service. My main computer is this one here. This is not advertising to any of these companies, by the way, it's just the tools I use. I'm not logging in most of these, but this is my main computer. I use paper space because when I'm training heavy models, big scale models, you can ensemble here the machine you want and you can rent that node online. So this is a cloud machine, but you can say, okay, maybe I'm starting a little bit smaller, just use one GPU, and then you can add more powers because your model is getting bigger, you have more data. And then you can add 4 GPUs and so on. You can go really crazy ensembling a computer in here. This service is the one I use the most on a daily basis, AWS, especially SageMaker. So in SageMaker, it's going to be a Jupyter Lab-like scenario. We will see about that. But mainly I use this one to have everything because lots of companies use this one and I do work with different companies. So to have everything in one place and you can train, deploy, and escalate your model in here as well. For my own personal use, my own experiments, most of the time I use Google Cloud Services. Sometimes I do have models that are training for days, weeks, or months, and you can keep this one in the background in the cloud training. It can get really expensive if you're not careful, but it's usually not so bad. And besides all of this, we also have Google Colab, which we will be using a lot. We will get familiar with this cell-based execution and IPython. You're gonna be using it a lot. But basically, this is a free machine from Google. They are giving you one for free. If you want more resources, you can obviously opt for a subscription. It's a paid subscription, but you will have more resources. But for free, they will give you a machine allocation from Google, and you can even choose the GPU. If you want these more advanced ones, you need to pay for them. But sometimes for small experiments, this T4 GPU is enough, and now you have a machine. You can even have a storage drive, you can upload things. There are pros and cons of using this, and we will see again this as we go. But those are some of my main resources, my main tools I use on a day-to-day basis. Yes, again, just to be clear, you can use your own local power of your computer, but once you need to escalate your model to big data, you will definitely need to be familiar with cloud services. That's how it works in tech, and that's how all the companies work. In terms of the OS, it doesn't matter at the end. If you're dealing with cloud services, the OS doesn't matter. You can even do it from an iPad or a phone. You're always using Linux in the back end. All the main development we're doing in AI is going to be Linux based. It doesn't mean you can't do that in Windows and Mac with your local power, but you will have some pros and cons and limitations of each. As long as you know how to use a terminal, you're good to go. Hello. Let's start with a quick introduction to Jupyter Notebook and IPython in general. When I open a new terminal, I will just use this to start the kernel, and it will work depending on your current environment and your current location. So let's take a look at the environments I have on this machine. Conda info envs for environments. It will give you a list of your different environments. For right now, it doesn't matter. I'm gonna stay in my default base environment, but obviously if you're experimenting with different libraries and different versions, and that's the reason you're creating different virtual environments, you need to jump inside the environment, and from inside the environment you need to run Jupyter Notebook. In this case, since this is just an introduction, I'm not using any special library, I will just use the default. But I will log in into some location in my computer, just to give you one example. Okay, so I'm in this folder at this location, some random place. The way you're gonna launch Jupyter, and I will advise you to create an alias for that, but you just type Jupyter Notebook, and then you can launch it. It will open your web browser, and it's gonna start a server and using a kernel in your machine. So if you take a look on what's happening here, I put it aside. Usually your login, your issues or errors or anything happening will be printed in the cells as well. But sometimes it's useful to have your terminal, and you need to have obviously because the terminal is running the session, but you will see the log info in the terminal as well. So I usually have them both side by side, or my terminal in some place where I can check what's happening as well. So in this location, since this folder is empty, obviously I don't see anything here, but this is already the main stage. From here, we can create a new notebook. So if you go to new, and in here you can see you can create a Python 3 IPython kernel, which is exactly what we want. And I click that, and this is Jupyter now. So if you never use a cell-based execution before with IPython, it's very simple and is one of the main tools we use in data science and AI development in general. Lots of things to talk about, but this is just a basic intro, and the more you use it later, it will become second nature. So in here you can name your document, let's call it test, and that's the name of your file. So from now on, our files are IPyNB for IPython notebook. So in here, you can already start writing Python. So for example, we can import libraries. It's exactly the same as using your regular Python terminal. So in order to execute the cell, you can press the key combinations Shift and Enter. And then when you execute this cell, this is the same as running a Python program. In the usual default Python, you have your program, you have your set of instructions, and then you need to stop working in order to execute until the point you are working in the current script. And the beauty about cell-based execution and IPython is that you can execute your code by chunks, by cell. So if I do in here, for example, print hello, Shift Enter, you can see the execution immediately after the cell. So you can see the printing in here. You don't have to get out of your program, you just basically execute that immediately. Let's start doing something else. In the way you use in regular Python, if you want to see the contents of a variable or things like that, you need to print all the time. In a cell-based execution, you don't have to do that. For example, let's create a new variable a. Let's assign 10, and then b to 20. C is going to be equal to a plus b. And now in here, I can just execute this cell if I want, and I can call whatever variable I have. Every time you're executing a cell, you're storing all of that in memory. So if I want to see the value of b at this point, I can just type b without using the print function, just type the name of the variable, and I can execute this cell, and it will give you the value of that variable. I can do the same with a, the same with c. So I don't have to rely on print statements all the time. That's the beauty of this. And now let's say I assign a new value to a, now it's 40. If I don't execute this cell and I go back here, obviously if you want to execute and see the content of two variables, you can't just do ca, that's not valid, right? That's an invalid syntax. In this case, you will have to print a, print c, in order to check those two. If I change something here, now that's in memory. This new value, this execution is in memory. So it doesn't work in the same order as a regular Python script will work. For example, I can go up here and in between insert a new cell. If you go insert cell below, and you can see the shortcut here, so you can go really fast A or B. If I check the value of A, you can see it's 40. Even when I'm here, where the value is supposed to be 10 in the regular order of Python execution. But that's the main thing I want you to think about. You're executing the cells and you're storing that in memory. So even when I change it way down here, it doesn't matter. It's what it's in memory, what it's counting at the end. That's called IPython, interactive Python. Similar way, if you're familiar with the Maya API, in Maya you can select a bunch of text and only execute that selection. It's really handy and is an extremely powerful tool. But as you can imagine, you're storing a lot in memory. So if you're not careful, you will end up using lots of memory. But this will be our main editor on this course, and we will be mainly using this one. So let's take a look at other functions we have in the editor itself. You saw all the cells, and you can insert a cell below, above. If you go here, one above, one below, and so on. You can also delete a cell if you hit D twice. And you have all those shortcuts and commands up here in the menus. You can cut cells, copy cells, do everything you want. And the cool thing is, since this is interactive Python, we can also plot in here. In the chapters about data science, we're gonna see about plotting and visualizations and dealing with data a lot. But we can straight up not just print something in the cell. We can have 3D plots. We can have all sorts of fancy things in between the cells. So it's a document for data science. Also, besides all of that, as you're working, let's say maybe you save this file, let's save this file, and then you're gonna log out and then stop your development. And then the next time, let's refresh this. Actually, let's just quit this. Cancel this running server and let's execute Jupyter again. It will obviously open this again. Let me close this. And in here, you can see my previous notebook. As soon as you exit this, everything is going to be wiped from memory. So if you open this and you try to execute here something, let's say, for example, let's do a NumPy array. Like that, this is going to fail. Even I'm not importing as NP, let's try NumPy. It's gonna fail. Even when you see all of these in here and you're importing everything, the cells are not executed, the cells are not in memory. So this is failing. It says NumPy doesn't exist because we haven't imported. So if you're doing something down here, you can always go back where you're actually calling in the libraries and execute that. And now if I jump into the last cell, this is gonna work. So I can see the contents of that container like this. So maybe all this stuff in between is experimental, and now you can see the true power. You don't have to execute all the code. This is a cell-based execution. Really, really powerful. So if you're down here, you can also execute all the cells at once by running everything. So if you go into kernel, you can see you can restart the kernel, the current session open, or if you go into cells, you can run all the cells. You can run all the cells below the current cell and so on. So let's run everything and it's gonna run. It's really fast, obviously it's just dummy data. But now everything here is in memory. So I can call in B and check the results of C and whatever I want to do. And again, I can jump from this to change the value up here if this was wrong, and I can go back there and execute only that. So that's a powerful thing about cell-based execution. Many different things we can do here, many different libraries we're gonna be working with, and different ways of using notebooks. But just be aware, kernel is the main running session. You can interrupt the calculation, you can restart your kernel. You need to be aware on which environment you're running your Jupyter session, and you have your libraries in there. As you're developing, this is really handy because sometimes you're going to be calling a library that maybe you don't have installed. That's why you have your library, your terminal at the same time. So in here, I can log in into that, I can jump into that environment and then just pip install whatever missing library I need to install for my current kernel. And you don't have to close anything or even restart. By just executing that again, you can have the library now in your notebook. You can check the help menu as well, lots of different fancy things in here, and you will get familiar with all of these down here as we go. We're gonna check pandas, matplotlib, scipy, numpy, and so on. You need to be really familiar with this because in a tech company, in the wild, in an actual development production company, you're gonna be using, if not Jupyter Notebook, a Jupyter-like editor and a Jupyter-like workflow. You will not be using that all the time. We use it every day in SageMaker for Amazon. We use it in Google Colab, and it's essentially the same because they're using the same technology in the backend. So obviously one of the main concepts is the information you have in between cells. Besides all the plotting, visualization, and all that good stuff, you can also, and you will see Markdown language. So if I insert a new cell here, you can change this from Python code to be Markdown language. So if you go into cell and cell type, you can change this to Markdown or row NV convert. I don't use that, I just switch between code and Markdown. So if you're familiar with Markdown language, it's just basically a text editor. So you can add comments or some titles. Maybe this section is to explore. You can execute that and now you have a title in between the cells. So you know this section from now on is to explore. and maybe you stop the exploration here. Let's insert a new cell. I'm going to change this to Markdown. You can see the shortcut is M. So if you know about Markdown language, you can use lots of different things for the syntax. You can Google about Markdown, but for example, I can give it a title here with hash and call this section data. And now we have a big, bold title for the next section. You can add all the documentation after the title. You can do all sorts of fancy things with Markdown language. And again, you can Google about Markdown language syntax. So it's all about dealing with your kernel itself. You don't have to go to the terminal sometimes to do different things. You can also do it in here. If you need to install a pip package, you can do it straight here, the same way you will do it, for example, in Google Colab. So with exclamation, you can run terminal commands, pip install and your package. If I do numpy, this is gonna fail because I already have numpy, but you can indeed run terminal commands in here. You can also run all sorts of different terminal commands. I can see my environments with this syntax, and we will see lots of different things. We can also time the cell execution, and the more we advance, you're gonna be dealing with lots of different terminal commands inside Jupyter, different ways of adding titles, different ways of visualizing your data. It's a really, really powerful tool. Okay, before we start, we're gonna do a quick refresher on some basic concepts and Python itself. Python will be the main programming language we will use in data science and AI in general. But it's not the only one. There is a lot nowadays with interactive, not just websites, but all sorts of frameworks in JavaScript. And most of the really powerful libraries will be done in C or C++. You're still executing most of those with Python, but if you want to go the route of creating something from scratch and really talking with your hardware, you can later explore C and C++-based libraries as well. Just to give you one example, NumPy is probably the core fundamental library we're going to be using, and the backend of NumPy is created in C. You're executing everything in the Python API, in the main Python framework, but the backend you're actually calling a C execution library. This happens a lot with many libraries and different approaches, but for now, let's forget about programming languages for a second and let's just start checking some basic concepts first. So first, you need to understand about APIs. This is really basic. I'm assuming you already know this, but just in case, again, we're doing this first chapter to level everyone up. So an API stands for Application Programming Interface, and it's basically that in-between entity between two services. Can be you, the middle point, and then some service. You will always see the example of a restaurant. If you're going into the restaurant and the whole program, the whole service is for you to have food, you are the client. The restaurant in the kitchen will prepare the food, and that middle interface in between will be, for example, the menu. So the menu in this case will be the API. In the API itself, you can perform a query, you can check the food, and your waiter or someone else will be in charge to pass that order around and to bring you your food. So you're posting a query, you have a response if the food is available, and then they will bring you your food. In an API works in a similar way, but you can perform more actions. So we usually split this in three types of API. You have web-based APIs, which is the most common one. You're talking to an endpoint, a web server, and then it depends on what this company is providing to you, you will have a response. For example, OpenAI, Hugging Face, Perplexity Labs, and many more. They will have a service and they will have a section for the API calls. For example, in here, this is replicate. We will see about this way later and many more, but basically every endpoint in a web server, you can see here the API calls I've been using, and you can search if you start exploring in here. Don't worry about this, we will use something like this probably at the end. But basically when you're trying to graph a model, for example one of these, and by the end you will know how to create one of these by yourself, and just a random one. If you go into the API, you can see there are examples for different programming languages. If we select Python, you will start seeing some common things that you need to be familiar with. If you haven't dealt with APIs before, we always have some sort of measuring. You will need to fetch for API keys so you can talk with this company or with the API provider. And then you will have some examples on how to call this API. And then you will have a response. In this case, you are communicating with the servers, using a model, and so on. The same will apply for OpenAI if you want to integrate, for example, GPT in your own company, in your own terminal. and so on, you need some sort of keys, some sort of login credentials to talk to that company for security measures, and then they will provide you with something. They will offer you something as a response. They are offering you some technology, some model, something. We're gonna do a little exercise with this page called JSON placeholder. It's just dummy data, but it's just for us to test how to retrieve something. So for example, in here, if this is the kitchen, they are offering us some sort of products. This is again dummy data, but we can call in this address and then we will have this as a JSON format as a response for our respective hash table. This is the case of a web API. We also have library APIs. These are basically provided by programming libraries, and these will be software-based APIs. So if you're downloading some application, for example, Houdini itself, the whole Python system in there is an API. That's the API for Houdini, so it has some Houdini-specific functions. If you're talking about Blender, Blender will have Blender-specific functions that the people at Blender created. That's an API for the software. And there are many more. When you're downloading libraries, packages, and whatnot, they will have its own API. So that's library-based APIs. And the last one is OS-based APIs. So let's say in one example, you're trying to create a graphical interface in Linux. You will need to call the OS Linux API called X11. As a standard, the X11 will be the graphical interface for Linux, and you need to call that one that the OS in this case is providing to you so you can have a graphical interface. It's not just for graphical interfaces. There are many more APIs that an OS can offer to you. So it's a matter of checking documentation, checking online, and what you can use with the OS itself. Maybe you're doing something Apple specific. Apple in the OS will provide you some specific API responses in order for you to do whatever you need to do. You can also split this in RESTful APIs. And basically RESTful APIs is a representation of state transfer. It's an architecture style. It's just designed for network applications. You're dealing a lot in this when you're dealing with servers and connections and you're responsible to create the backend side of a product. They are called RESTful because they are designed based on the REST principles. And in the standard HTTP methods, you can basically get data, you can post data, put and delete. So if you are the one dealing with the data in a server, imagine when you have a data set for your company or for your product, chances are it's not going to be a fixed data set. So if you're the developer in charge of doing this, you will be following these principles. You can post new data into the data set. Maybe you can delete some entries that are making it really laggy and heavy and you don't need them anymore. You can mutate that data set. So you have these controls to basically manipulate the data in the servers. It's also useful to get familiar with some of this, because you will be communicating with a lot of web-based on server-based APIs too. So just for example, when you have some code like 200, this means that everything went okay, and then you have your response and you can log in these codes. They are standard when you're dealing with servers. 301 means the server is redirecting you to a different endpoint. When you're retrieving something from a web server or from a server, for example from here, this is called an endpoint. The same with this when you're dealing with different data and API calls. You will be fetching an endpoint which will be responsible to give you that response you need. In this case, it could be the case that for some reason it's not fetching the proper endpoint, but they do have a backup or a new version for that. So 301 means it's going to redirect you to a different endpoint. It's very common when you're switching domain names or the endpoint name has changed. 400 means the server thinks you did a bad request. You can have a typo or something is wrong in there, but it will give you that log in the form of this error code. Now, 401 is usually when you have bad credentials and things like that. So the server thinks you're not authenticated. It will depend on the API call and the endpoint, these levels of authentication, and they will be different pretty much all the time. 403 is mainly a permission issue. So what you're trying to find, you're trying to fetch from that endpoint is known as forbidden, which basically means you don't have the right permission to see this. And 404, the server didn't find the resource you're trying to access, so it doesn't exist. It can be deleted or for some reason, or you have something wrong in your code, but basically 404 is not fetching that endpoint successfully. Assuming you have requests in your virtual environment, we can just import that. Now that we have that, we can do an API call. So let's do a constant here. And let's paste this address from JSON placeholder. So that's our main URL. And then we have a variable called response. And that's going to be equals to request.get. We're just getting that information. And the URL will be equal to that constant. Finally, we can print response.json as a function call. And if we execute this, we have all the data in here. For us, will be in the form of a dictionary, but it's basically all the data you have in here. So now you can perform different kind of needs. If this is real world data, maybe you don't need all of it, and then you need to section, and it's just a way of manipulating your hash table. So one of the most important libraries we're going to be checking is, first of all, NumPy, the core fundamental library for our entire development. Probably we're going to jump in and out from NumPy, or NumPy will be in the backend of most libraries, but it's really important to have a grasp. Later, we will have a tutorial, an introduction to just NumPy, and a bunch of other these libraries, especially when we're dealing with data science in the data science chapters. For now, just be aware we're going to be using NumPy. Pandas will be extremely important, and we'll probably use this pretty much in the entire course. Matplotlib we're going to use for visualizations, and once we kick in the really cool visualizations, we're going to jump into Seaborn and other. But for now, just to keep you aware, we're going to be using multiple different libraries for our needs. We'll try to implement everything from scratch, but then we're going to jump into other frameworks like scikit-learn and so on. Don't worry about all of this, we will check one by one as we go. For now, the most important thing to realize is the most common file formats for data we'll be using at the beginning. Those will be either from API calls or straight up downloading our datasets to check some experiments. Our main stage for this will be Kaggle. At the beginning is one of these big main standard repos for datasets. So if you go into datasets, all sorts of datasets for different things, computer vision, NLP, you name it. Kaggle obviously not the only one, but we're going to be focused on this the most. For now, we're just going to worry about two kinds of data entries and data formats. If we start checking some of these, most of the datasets we're going to be dealing in the wild will be in CSV format. That means comma separated values. And it's a very common and standard way of working. If you check any of these, you'll probably see a table. If you haven't worked with CSV files before, it's very similar to Excel, and it's one of the main formats you're going to be using all the time. For using this, we already have a library in Python for the CSV files, but it's not very used in an actual production. So for mainly dealing with CSV files, that's why we're going to use pandas. This is not a tutorial yet about pandas, it's just for be aware that we're going to mainly be dealing with CSV files all the time. And we probably need to convert and mutate and really know how to navigate through CSV files. And the other format, once we're performing API calls and whatnot, will be JSON. So JSON files and CSV files. You really need to know how to navigate in those files and how the structure is working in the backend. We're not going to go in a tutorial about JSON. I'm assuming you already know that, and you can search online if you're not really familiar. In Python, this will be a dictionary at the end, keys and value pairs, but you need to know how to navigate through the values or just fetch the keys, or some sort of navigation algorithm where you need to traverse and fetch some data from a JSON file. You need to know how to create JSON files, how to update JSON files, and so on. If you don't know that, just Google around for JSON files in Python and you will find everything you need. This is just a quick video for me explaining what kind of libraries are coming in the future and what kind of data format we're going to be using. So besides CSV files and JSON files, as a very basic intro to dealing with data, the main data we're going to use in production will be SQL databases. So we're going to learn about SQL later. And there are many more types of data. So let's talk a little bit about data gathering methods. We're going to be dealing a lot with this. One way of doing this, and the way it was done in the past in history, was with surveys and questionnaires. Obviously that's not very reliable and it takes a long time to collect the data, but you can still use it for nowadays. The other way we're going to check is with web scraping. Web scraping, because not all the time you can download your dataset. Keep in mind, in the production scenario, it's not like you're using your local machine all the time. So you need to straight up read the data from a URL, and you can read tables by doing web scraping. And sometimes you need to gather lots of data in batches, and it's going to be impossible to do it manually. So you need to create some sort of bot or program that goes into the web and scraps for data. Really useful. Libraries for Python will be, as a standard, Beautiful Soup. So if you check the documentation for Beautiful Soup, we will see about this once we start using it and scraping data from websites. But in the meantime, you can check the documentation and have it installed. Beautiful Soup is extremely efficient, and there are many ways of doing web scraping, but we're going to be using this one mainly. Besides that, we already talked about APIs, how we can access different endpoints to collect our data or any other information we want. There's all sorts of data. We can also start talking about sensor data. If you're monitoring weather, for example, from different sensors, this will be real-time fetch data. Or if you're reading, for example, temperature from servers in your company, this will be real-time data as well. There's so many things in data itself. We will see that in time in our data science chapters. This is just an introduction on what's coming and some common libraries in file formats we need to use. All sorts of data as well can be observational studies. There's already so many papers published by many different entities, many different companies or people that you can take advantage of because they are public and is meant to be used for your experiments. As discussed before, the main file formats will be CSV, JSON file. In production will mainly be probably SQL databases, and we will see way later about that when we start dealing with big data and big query. And there are others. Just to mention you a few, there's something called HDF5, Hierarchical Data Format version 5. There's also Parquet, Avro, Feeder, Pickle, login files, text files like TXT for logins, and so many more. We're going to be using some as we go and our needs to save some files. Sometimes we need to package an entire model or an entire piece of code so we can reuse it. So caching, we will see about memoization, we will see about serializing for pickles, for example, and so many other ways. And there's obviously the most common data types you're probably using all the time, like audio, video, images, and so on. Just for you to be aware, there are many types of data, and depending how we need them, how we read them, and how we interact with the data itself, we can be changing from one to the other and packaging and distributing and working with the data itself in different ways. Hello, so let's jump to the good stuff. We're gonna start with a little bit of calculus, and one of the most important concepts you need to know is derivatives. One of the main mathematical functions and mathematical ways of calculating what we will need a lot in the whole field of machine learning and AI. We will check why do we need to calculate the derivative and what the derivative is. If you search online about the derivative or any research paper, you will see it in two ways, in physics and in geometry. For us, we care about geometry because we're going to be dealing with geometric shapes, lines, angles, triangles, and so on. So for our needs, the derivative we're going to calculate and we're going to learn about is going to be geometry based. So in this concept, what we mainly care at the beginning will be to calculate the slope of a line. And let's check why, and let's check a quick example. So let me do a new layer here. Let's say we have two particles, particle A and particle B. We're assuming particle A and B, they have a constant velocity, and we're trying to figure out the speed on which they go. So we have some data about time and distance. Let's calculate that. Let's do some coordinates here. Now, for particle A, let's assume this is t for time. So let's say these are seconds, 1 second, 2 seconds, and so on. And the distance we don't know, can be like millimeters, centimeters, but these are units of distance, so this is d. Let's say particle A, for each second, it's moving 2 units of distance at the time. So the coordinates with this will be a point here. So we can say the representation of the function for d, if this is 1, we can say that d of time, d of 1 of time is going to be equal to 2 times the time. Because if we move another unit in 2, this will be 2 times the value of time, which will be 4. In this case, the point for this will be here. Therefore, we can assume this function is correct. So if we draw a line here, this will be the representation for particle A. And our job is to calculate the slope of this line, which basically means we need to calculate this angle here. Now this angle will be alpha. And how do we calculate this? Before we do that, let's just quickly do it for B as well. Now for B, the representation of this function will be d2 of time will be equals to, let's say, 5 time. Remember, this is t, this is d, so distance and time. In order to represent this in our coordinates, if d is moving 1 unit of time, which will be 1 second, the units on distance will be 5. So we can draw a line in here. So obviously, if we have 2 seconds, it will be 10. So we can see those values. Now, if we take this, so I'll just put this in a side here. If we draw the 2 at the same time, let's do another of these coordinate. So for A is red, for B is blue. You can see the difference in how the slope is behaving the more we advance in distance, even if we have the same time, the same units of time being calculated. What we need to calculate is the tangent of this alpha angle. And the way we're going to calculate that is by using the gradient. Before we jump into that, let's quickly explain what's happening here with these lines. So if you have another line that's going in a linear way, for example like this line, let's assume, is the basic equation of a function of a line. So for example, is f of mx plus b. This is very familiar, is the equation of a line. In our case, you most of the time will see this as y equals to mx plus b. Really important for later. This will have to do with the weights and biases of a neural network, but we will see that way later. So for now, the basic equation of a line, we can interpret that as this, which will be this line here. So if we move this line, if we start with the angle, let me do another color here. So if you take the line and at the beginning everything is 0, so it's flat at the bottom, the tangent of the angle will be equals to 0. So if alpha is equals to 0, then the tangent of alpha is also 0. Now, what happens if we start to increase this alpha angle? So now let's say we're just moving this in this direction. The range of this will be between 0 and 180. So remember that. Let me do another color here. This range of this motion will be between 0 and 180. So let's take a look at that. If you keep moving this alpha angle in this direction, this value of tangent, the tangent of this alpha angle, will start increasing. Obviously, I don't know exactly the mathematical value. I'm just drawing lines in a random place, but this value here will start to increase. This is called an ascending. This is called a positive or an ascending gradient. So if we move it more, maybe at this point the same one as here, this value will increase more, and then we keep moving this line and so on. If we reach this point where it's perfectly 90 degrees, this value will be undefined. Basically, we're defining this as undefined. It's not defined yet. But what happens if we start going more than 90 degrees? So we start going into this direction now. What happens is this value, the tangent of the angle, will start going into negative. And this is called a descending gradient. You're going more and more into this direction, this will go into negative until you flatline again, you reach 180 degrees, and this value will become 0 again. So this is what's happening when we're doing this. Really important because we're going to be using this a lot. And you will get really familiar and remember this once we reach the gradient descent algorithm. But basically the motion of this is what determines the value of this tangent. Now, in order to calculate this, you're going to do it with the gradient. The gradient basically measures the tangent of this inclination angle. Okay, it's time to calculate the gradient. We're trying to calculate the tangent of alpha, of that alpha angle. So if we let's check A again. Let's quickly draw A. But this time, we're still taking A. Let's draw different values for A. So let's go into 3, which will be equals to 6. It's moving 2 units at a time. So we still have the same line. This is still for particle A. So if you have these two new points, let's do a point here, point here. Obviously my drawing is not extremely precise, but you get the point. The way we're going to calculate the gradient is we need to extend this line until we reach this line crossing over. And if you can see that, we have created a triangle. With this geometric shape, we can calculate everything we need. So now that we have that triangle, if this angle here, alpha, is the one we need to calculate, since this is a straight line, we can know for sure this angle in here in this triangle will be the same. So it's still alpha. The way we can calculate that, now we are in basic trigonometry because we are calculating the sides of the triangle. So how can we calculate this? This distance here will be equals, if we assume in the first point, which is 1, that we can mark that as x1. The next point, we can mark that as x sub 2, x2. The measurement of this side will be equals to the subtraction of x2 minus x1, right? Really simple. So here is x2 minus x1. So the points in here for the original triangle will obviously be y of 1 and x of 1. Remember, this is x, this is y. So this point in here will be equals to x of 1. And if this is y, this will be y1. So that's y1. We can establish the next point in here to be y2. And obviously the one in here will be this one down here, which is x2. So we have those two values, x2 and y2. By subtracting x2 minus x1, we have this value. And in order to have this value of this side of the triangle here, it's really simple. We do the same. We just subtract the distance y2 minus y1. So the formula for the tangent we're trying to figure out is indeed the tangent of alpha will be equals to y2 minus y1 over x2 minus x1. That will give you the value we're trying to calculate. And this is how we calculate the gradient. Remember this. If we take a look at these values down here, x2 minus x1 will be 3 minus 1, that's equals to 2. And 6 minus 2 for the other side will be equals to 4. So if we translate this formula now, tangent of alpha will be 4 over 2, which is equals to 2. We have calculated the speed of the particle, and we can say if the units in distance, which is d and time, distance and time, let's say these are millimeters. Obviously a particle possibly maybe it doesn't move in millimeters, but let's say these are millimeters. We can effectively say that it's moving 2 millimeters per second if these units of time are seconds. But we have calculated the speed of particle A. You can do the same for particle B, and now we know the speed on what the particle is moving. Okay, now that we understand the gradient, it's time to move it to a more realistic approach. Let me hide all of this. We can still keep this visible. It's helpful to know where we're coming from, but in the main case, in real life data, it's not going to be a straight line, a constant speed, or a constant movement, or a constant exponential growth all the time. So let's draw a more realistic graph. Still for particle A, in reality, a particle is not going to have a constant motion. So let's talk about why. Let's say this particle A exists in space and is moving in some direction. Maybe it's moving really slow at the beginning, and then it goes up, it goes down, it goes really fast, it stops for some reason, maybe it can even return. But speed-wise and distance-wise, you're not going to have a straight line as most cases on real-life data. So let's draw some example. Again, this is time and this is distance. Let's say this was the particle movement. It started really slow and the distance will be this angle here. So for example, if you have one point at the beginning at 0 and let's say another point here, we know this is going to be the distance. But as you can imagine, it's not going to be the same from 0 until this point because the distance is going to be now this portion here. That distance indeed is changing a lot depending on the speed of movement of the particle. So as you can imagine, in a case like this where we don't have a straight line, how can we create one of these triangles so we can calculate the gradient, so we can calculate therefore the slope of this function? We can do that as an average And let's take 2 points here. If you randomly take 1 point here and another point here, we can indeed draw a line like this. This line is called a second line. The second line, now that we have that, we can create that approximation, because we can do exactly the same if we draw and calculate the gradient of these points. If we create this triangle again, we can indeed calculate the slope. But what we're trying to do is, remember, we're trying to figure out the tangent of this gradient, not the second line, because we have a second line by doing this. So how can we transform this? And this is the power of the derivatives. This is how we calculate the derivative. So let's take this point. Let's call this point point C, and this point up here point G, so we can have some names for the points. If we calculate these delta values, let's call this side R, and this one will be W for the triangle. The point where are we calculating this second line and we are effectively creating a straight line so we can have a triangle, there will be a values in X and in respecting to Y. So all the graph you see here, this main line, this line is a function. We will define that as a function in math. So effectively we can say the points that are being calculated in order to have point C in X and Y will be, let's call this one X, right? Which is some point around here. Maybe it's exactly 2. And we know the distance in order to have the next point, maybe it's not exactly 4, as you can see, it's right before 4, but we can denominate this as X plus H. Now this H value will be one of the most important values in your entire career in AI in general. So remember this one, H is gonna become something really, really important down the line. But this value, indeed, this distance between these 2 points, the first point is X and the second one is X plus H, which will be indeed the size here for R. And for the other point, if the value in here, we can denominate that as the function of X, the second value here in the y-axis will be similar, the function of X plus H, which is this distance from here to here. Now, given these values, we already know how to calculate the gradient. So let's pass that into our formula. We're trying to calculate these values here. So this will be the differentials, will be equals to the values we have in here. Remember, it's the same thing we did calculating the gradient before. So that will be equals to the function of X plus H, this value here, minus the function of X, which is this value here, right? This distance here. All of that we over these values in here. So we're taking this value first, which will be X plus H minus this value here, which is X. As you can see, this one will cancel each other. And now we are left with this. Now that we have that, we can calculate and we know the gradient of these 2 points, but this is still a second line. How can we transform this into a tangent line? And this is the really powerful thing. Why this value is so important. If you take a look at all these functions and formulas, pretty much everything is driven by the value of H. So if we move H, let's start doing this in a positive way. Let's start increasing H. Remember, H is this distance here. X plus H will give you that distance, right? The same thing will happen in here. So if we notch H, if we move the value of H, all of this will change. And effectively, if we just move that, now we are changing this position in here. So if we start increasing this in a positive way, this one will travel along the line. So let's say we keep moving that value, we keep increasing that value until we reach, for example, this point here. Now we have a new line, something like this. Therefore, our new value of H, it will be something around here. And this one, well, this one is almost exactly the same, but maybe the point was up here or something. You see how we are changing this? In this case, they look very similar as the original value in Y. But if we keep doing that, let's move this point now in here. Let's do another color. Now it's more like that. and this value will become x plus h someplace down here and someplace up here for y. Still a second line, but we can calculate these gradients every time we're moving something. So for this new one, the triangle will be something around here. So what happens if instead of increasing h, we decrease h? Obviously, if this was our starting point in here, we are going in that direction of the curve. So maybe now this value, let's say, is around here. This is getting really messy, but you get the point. We are moving along the line by moving h. So let me draw a new graph with this. So let's say we have a function like this. The curve looks different, but still different velocities and stuff like that. Let's pick up 2 points again. One here and another one up here. We know the formula. This is gonna be f of x. So we know these formulas. If we start decreasing the value of h until we almost reach 0, we will never reach 0, otherwise we can't do the gradient, we can't have the triangle. But if we start dealing with tiny values for h, we are moving h in this direction in here and down in here, we will almost merge them. They are tiny values that they are almost the same. This is really close to 0. In mathematics, this will be like almost like an infinite value. Now we can have a line that is basically a tangent. So if these points almost merge and become 1 point, now we can calculate at any point in the curve, in the function, in the graph itself, we can calculate the gradient. Therefore, we can know the speed of the particle at any point we want in the graph. If we start moving these values, and maybe we're reaching 2 points here, I'm drawing just as 1 point, but you get the idea, they are almost merged together. We can indeed draw a tangent line and calculate the gradient at any point in here. And that's the derivative. Extremely important. This is just the basic introduction. There's so many more things in derivatives, and I will advise you to investigate in integrals and more about derivatives itself, differentials and so on. But by having the power of calculating every single point in the graph, and we will know the speed at any point in the entire curve, we will know, we can basically travel back in time, and we will know exactly the speed of the particle at any point. I cannot stress this enough how important this is. With these calculations, we know the speed on what the Earth is moving. With these calculations, we know the planets are moving around the sun. With this, we know how to launch rocket ships into space and calculate the trajectory. We can calculate the trajectory of an asteroid. Basically anything you want. So indeed later, in some graphs we will see, let me do a quick one here. If we have a graph like this, let's say in our calculation, we landed at some point, at some random point in here. And our job is to find the minimum value in the y-axis, which visually I can see is here. But for the algorithms, for a computer, we will need to move this point the same way we're doing it with all these calculations in order to find that minimum value. So we will deal with h. We will increase h and we will see what's happening with the slope, with the gradient. Are we going up? Are we going down? And by how much? This is how powerful this is, and this is the core fundamental mathematical operations in not just in AI, as I told you before, in pretty much all science. So maybe we start dealing with a negative value in h, therefore we start moving in this direction. So we're going down, we're going backwards, and we reach this point. And maybe this is a point we're trying to fetch. But what happens if we change the direction and start going in positive values for h, and we are moving in the opposite direction? This time we are moving this way, and eventually we will land up here, and we will compare that indeed this value is lower than this other value here. And this will be our new correct value. If the algorithm we're trying to do is to find the lowest point in this whole graph. Really important. Again, this value h later will become something for us called the learning rate. Once we reach this, you will know where all of this is coming from and how we can calculate the gradient, the learning rate. But again, h, one of the most important values in this whole calculation. And now we can basically travel back in time. We can calculate speed of vehicles, particles, not just speed. In our specific case, we are calculating the speed of the particle. This can apply to anything. To give you one last example here, with some data, some random data. This is an example a teacher once gave me. So let's say we have some points here. And this will be the data points on when my dog wants to go outside. So the desire of my dog going outside, and maybe this data is weather. So if this is like almost 0 degrees, the chances are my dog, if this value here, this first point, at this point maybe my dog doesn't want to go outside. It's always in his bed or something. And maybe in here it's kind of thinking about that, and maybe in here at this point it's okay for my dog to go outside, right? But if we keep the graph like this, and again we're dealing with a linear value, this data wouldn't be correct, because if we keep increasing data points, this is telling me the higher the temperature, the more my dog wants to go outside, which is incorrect, because if we keep just growing this exponential, we can reach temperatures like the sun, which will be incorrect. Obviously, at some point, my dog is going to be too hot and it doesn't want to go outside. So if you just think about this data, a more realistic graph will be still exponential maybe at the beginning, but at some point maybe it's flatlining and maybe it's too hot and my dog wants to go back inside. So that's why the data is almost never linear and the data looks like this. In this case, we were trying to figure out at any point the desire of my dog wanting to go outside. So as you can see, it's not just about speed. We can do this with any kind of real world data. Okay, let's try another example so we can really take this home. We have this function here. F of x is equals to x squared plus 3, which in the graph, it will look something like this, right? This is the function and those are the values. So we have the point and the coordinates for the first point, which will be 1 and 4. And for this second one will be 3 and 12. We have these points. In order to calculate the slope for this function, we already know we can draw a second line. So if we draw that line, something like this, we can calculate the slope of this with the formula that we already know. So the slope and the formula we know is y2 minus y1 over x2 minus x1, which if we translate those values, we know this will be 12 minus 4 over 3 minus 1, which will be equals to 4. That will be 8 up here and 2 over here. 8 over 2 is equals to 4. So the result, the slope of this line is 4. Right, we already know how to do that. So let's calculate step by step the derivative of a function. If we have this time a function like this, let's deconstruct this step by step, but this time using the derivative. So remember, we need an h value in order to calculate this. So by incrementing this by tiny values, we will have the following. So if we now have the function similar as I showed you before, which is x plus h, will be equals to x plus h to the square. After we apply the slope formula to this, we will have f x plus h minus f of x, which we already know that, and this is over h. We saw how we deconstructed this until we reach this, and if we simplify this, it will be x squared plus 2xh plus h squared minus x squared. We know this will cancel, but let's make it complete. This is over h, and now if we simplify this, we know this will cancel each other. We have 2xh plus h squared over h, which is equals to 2x plus h. Now, if we start sending h to the limit, which the limit we know is going to go towards 0, we will have 2x plus 0. Let's say we're reaching the limit, it will be equals to 2x, which basically this means, the result of this means for the function f of x equals to x squared, the slope at any point will be equals to 2x. This is what this formula is telling us. So indeed, the formula of this can be defined, and you will see this a lot. You have the limit of h going to 0, which this is f x plus h minus f of x over h. That's how we are defining this. So using all of this, now let's jump into Python so we can code our own derivative function. So let's start translating this. Now define a new function. We want to pass in indeed a function. We want to pass in a value of x as well. And h will be equals to some number. Let's start with 1.2, something really high. We're going to return, and you can see the formula in here indeed is this one here. So the function, and we see those values here, will be equals to x plus h minus the function of x divided by h, which is what we have at the end indeed in here. So I'm basically just recreating this. If we create another function to actually create those functions, f of x will be equals to, we're just gonna return x to the power of 2. That's our x function. So if we start adding those values, so x, let's start x with 3. Our computation for the derivative, let's call that cd, will be equals to the derivative function. And we're gonna pass in f and x, right? The actual value will be equals to 2 times x. And now let's check at that computation of the derivative and the actual value. So we can just print it indeed. You can see the value, obviously it's way higher because we are using an unrealistic value for h. So this is way too big. Let's start decreasing this value. Let's just try 0.1 and let's try this again. Still, the value is really high for what we need to know, but you can see it's really close. But the value of 6.1 is still far off from 6. So let's do this really tiny and let's see how we are affecting that. Now you can see this is closer to each other. In this first function up here in the derivative, we are computing the derivative of the function at any location. The location will be the value of x. This will be the step size. Again, for us later, that will become the learning rate. And this is the result, as we can see in our formulas here. So by defining another function, which will be the result of the function x, we're just taking whatever value and raising it to the power of 2. In this case, our value is 3. And we are passing that into our derivative so we can know the location of x in respect to the function. So this is telling me the actual value we have, and this is giving me the location by calculating the derivative. The main use case we're gonna check this later will be when we are checking the optimization algorithms like gradient descent. But now you know where all of this is coming from. Hello everyone, let's move to the next chapter. We're gonna check about integrals. One of the core fundamental operations in calculus, in AI, machine learning, whatever kind of scientific field you're trying to get into or explore, integrals will be one of the main parts and operations you will need to know. It's important to know it in depth. I just do like a high level overview. It's not like you're gonna be doing by hand this all the time, but it's gonna be very important for you to understand why we're adding and checking different parts of calculus. So let's take again the same example as the particle. We have a particle and the particle is moving at some speed. So let's do the coordinates. This is t for units in time. And in this case, y will be the speed of the movement of the particle. So this can be centimeters per second. Okay, so these units, let's have here like 5, 10, 15, and so on. And in time, we are moving in seconds. I'm not doing everything, but let's say this one here is 7. So at 7 seconds, let's go to the simple example again. If we assume the particle is moving in a constant velocity, it will be the following. If y in here is the speed on centimeters per second, it's always going to move at the same rate. So if we graph something like this, and it would say in 7 units of time, in 7 seconds, maybe it's moving at the speed of 10 centimeters per second. So this will be constant all the time and will flatline like this. And if we project that, we have this graph. The distance from here to here, we know is in time, so that will be 7 seconds. And from here to here, we know that's in centimeters per second, so it will be 10. As you can see, this is assuming the velocity is constant. Therefore, we have created a rectangle in here. Now, if this is time and this is speed of centimeters per second, the way we know the distance traveled by the particle will be to calculate the area of this rectangle inside here. And the formula is extremely simple. We just multiply these dimensions. Height times width. And 10 times 7 will be equals to 70 centimeters on where the distance of the particle is moving. So the particle travels 70 centimeters in this specific point in our data entries. That's how we can calculate this. Really simple, and in an ideal scenario this will never happen. It's not realistic because again, the particle is going to move at a different speed. It's never going to be constant. So how can we approach this? Let's draw new coordinates, and in here let's draw a more realistic function for the particle. This will be function of x, and it can look something like this. Start at 0, maybe it's ramping up, maybe it's going down, up, and so on. So in this case, this is a more realistic approach on how a particle will move. We still have some units, which will be the same. This is t for time, and in here we're gonna denominate this again as the speed on centimeters per second. Each one of these values will be the seconds in time, and the values in y will be the speed on centimeters per second, the same as the graph here on the left side. So how can we calculate the area under a curved surface? It's really easy when you have linear shapes, when you have geometric shapes like a rectangle or triangle, but what happens when you have a curve, which is what we will have most of the time. In this function of x, which is this curve here, let's try to do some approximations. And how can we tackle this issue? What we're gonna do, let's do some section. Let's choose 2 points. Point A in here and maybe point B in here. We don't know these numbers. Maybe again this point is 7 seconds. But we're gonna choose a section. So if I project this one up, now we are effectively in this range here, and we need to calculate the area inside down the curve. That's how we're gonna deal with integrals. But how can we do that if we have curved lines? We can't just take area units like this one here. So the way it was done in the past, the way we can do an approximation is, instead of having one rectangle like this one here, we can have multiple rectangles. So let's do that exercise. Let's draw a rectangle here, and now we have 3 rectangles for that range. We can calculate the area of each one of these, which will be the area of this one. Let's call this A1, A2, and A3. If we sum these areas, we will have an average, an approximation on the area in the section we're trying to find, right? So how can we know the size of each one of these sections? In this case, we are straight up taking the units per second. But if we want to do a better approximation, we'll have to do it in a different way. As you saw before, by having rectangles in here, like these ones, there is a lot of gaps everywhere. We have gaps here, 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 here. So we have an approximation globally, but the results are not too exact. So in order to have a better approximation on this area, we can have more rectangles. So instead of having those 3 in this section of A until B, let's add more. Obviously my drawing is not perfect, but you get the idea. If they are perfectly straight, we can fit more rectangles inside, and we can calculate those areas and have a better approximation on the whole section we're trying to find. But we still have lots of gaps in here, which can be an issue if you're trying to be precise. So how can we know the width of each rectangle? If we do some sections here, like this, besides the unit of second, the way we're gonna draw those rectangles, like this for example, we're gonna call the width of that delta of x. How can we calculate those? If we subtract b minus a, and we have the absolute of that, it will give us a range. It will give us this distance here. And by the total amount, we're gonna divide that by n. N, the number of segments. We don't know how many segments are we creating here. Can be 5, can be 7, can be 1000. But the formula is indeed to find out the delta of x. Each one of these sections here is gonna be b minus a divided by n, and the total number of segments. So indeed, as you can imagine, in a similar way we tackle the derivative. What happens if we start lowering the value of n towards the infinite? Really tiny amounts. Therefore, we want to fit more and more rectangles in between. We have so many numbers in there that we almost fit the entire range we're trying to find, all in here. So in this case, it will look something like this. We will have lots of different rectangles inside. Each one we will have an area, right? So A1, A2, A to N. It will be a representation like this. So the total area we're trying to find, it will be the sum, because we need to sum them all, of N. I is going to start at 1, and the function of X sub I. Each one of these segments will be X1, X2, X3, X4, X5, and so on. So X sub I, for each iterator in there, is going to give us the delta of X. In a more mathematical way, what we're trying to do, you will find a formula like this. The limit of N as N goes to the infinite, which is the sum, and the same as above here, when I is equals to 1, the function of X sub I will give us the delta of X, which pretty much the main way you will see this in an integral formula will be with this symbol, the big S, where we have the 2 points, right? B to A. So all that range in between here, we're doing the sum of all of those function of X and the differential of X this time, which is basically the same thing. We will have an infinite amount of rectangles inside, so we can sum all the areas, and we will have the area below the curve. But as you can imagine, if we need something absolutely precise, we're still having these gaps in here. So is there a better way to calculate the area without even using rectangles? Because sometimes, and especially in AI, we need absolute precise values. The more we want our machine to be intelligent, the more precise it has to be. How can we tackle that after seeing all of this? Let me do a new graph. Let's start with a simple example. This time we will have a linear graph, so we can see the units better. And this time the function will be f of x is equal to x, which you can also interpret this as y is equals to x. This is y, this is x. So if we have some units here and here, let's start doing this. Y is equals to x. Wherever x is, y will be there as well. So it's going to be like this. And at the end, it's going to be a linear straight line. So all these points will be intersecting here. That's basically the function we're drawing here. This is f of x. We're doing it like this because it's going to be easier for us to identify what we are trying to do. So this unit in here, let's add some numbers. So this is 1, 2, 3, 4, and 5. Again, I'm doing a quick drawing. This will be absolute mathematical perfect in between. And obviously the same in y. Now we know this projection will be like this because y is equals to x. We have that point in there. The same for all of them. Now we can establish the way we're going to calculate the surface below this curve will be in area units. For each section, we need to calculate the area. So how can we define an area unit? It's really easy here because they are the same. So it's going to be 1 unit, right? Take a look what I just did here. I just created basically a square in here. And all of this is 1 area unit. So in here, what we have below the curve is the exact half of 1 area unit, which we can represent that as a numeric value of 0.5, which is the half of 1, right? Let's move to the second one. 2 will project here, and in y it will be here. If we keep extending this, now we know if this whole square here was 1 area unit, now in here what we have is this. By the time we reach 2, in this case, let's count everything we have in here. We have 1 full area unit, and if we join these 2 halves together, it will be another unit again. So now we have 2 area units, which we can represent obviously by just adding 2. By the time we reach 3, let's do that again. And now what we have in 3 is 1, 2, 3 full area units. This one with this one will be 4th, and this one is a half. So it's 4.5, which we can do 4.5. By the time we reach to 4, let's do that again. If we count them, we will have 1, 2, 3, 4, 5, 6. This one and this one is 7, and this one is 8. So we have 8 full area units, and we will have 8. And when we reach the last one, let's say the segment is until 5, you will have it like this. And if you count them all, will be 12.5. So let's analyze this pattern we have with area units. In 1, we can say is 1 square over 2. If we square 1, it's going to be equals to 1. 1 over 2 is 0.5. So 1 divided by 2 is 0.5. Let's do the next one. 2 is going to be 2 square divided by 2. 2 square is 4 divided by 2 is going to be 2. 3 is 3 square. Notice this pattern, the same number always repeats, but we are squaring that number. And it's always going to be over 2. 3 square is 9. 9 over 2 is 4.5, so we got that result again. 4 square, 16 over 2 is going to be 8. 5 square, 25 over 2 is 12.5. So this pattern is extremely important. Therefore, we can represent this whole thing, every value in x, the result is going to be x squared over 2, as we can see for each one of these, which will give us the area we're trying to find. And if we add them together, we will find the result we need at the end. So now that we have this x squared over 2, what can we do with this formula? What can we do with this function we have here? We know that we have this function x, and now we have this one here, which is x squared over 2. There is a relationship between these two. And if you dig around more about derivatives, you will know something that's just clicking right now. Let's do that one again up here. X squared over 2, and let's have the other function x. This function here, up here, will be the integral of x. And if we derive this up here, this function, the result will be x again. So we are coming back. And this is the magic formula about integrals. If we have a function, x, for example, if we find another function like the one up here, where if you derive, you come back to the original function, you have calculated the integral in one side, and you have calculated the derivative in the other side. So they are the opposite. Therefore, with this magic formula, you can calculate the areas on anything you want. And we will do an example of that in just a second. But let's derive this function up here. Let's just take x squared. Let's do this in one side. Let's do it up down here. We know that the derivative of x squared, we just basically have to move the exponent as the first element will be equal to 2x. That's the derivative of x squared. So how do we know this cycle here is indeed happening? What we have here is we can represent this as y is actually this formula, x squared over 2, which is the one we're trying to find. In here, so that we don't get confused, I don't mean like x is equal to this. Just the result of everything we're doing will be equals to this. X is these values here, 1, 2, 3, 4, 5. But in this case, we're going to represent y as this, and let's do the derivative for this one. So what we're going to do here is, how do we do the derivative for that? We know that just for x squared is going to be 2x as a derivative. So for the numerator, the formula we know about the derivative, and the way I did in the previous video is, if we do just this, x squared is going to be 2x. This is the derived version of the numerator. We need to multiply that by the denominator, which is 2. And then we need to subtract from there the non-derived version of the numerator, which is x squared, times the derived version of the denominator. In this case will be 0. Okay, so if all of that this time over 2 squared, the result of this will be 2 times 2 will be 4. This operation here will be 0, because if x is whatever number x to the exponent times 0 will be 0. So all the result in here is always going to be 0. Therefore, we can cancel all of this and we're just left with this expression, which will be 4x. And for denominator, it's going to be 4. 2 to the power of 2 is going to be 4. We know as we divide that, these are going to cancel, and the result is finally just x. That's how we know this indeed is working. The derivative of this will go back to the original function. So how can we use this? By doing this, if we have a case that y is equals to x, we know by doing all of this, we know that x, by the time we do our integral and derivative, is going to be the formula we need is the one we just calculated, which is x squared over 2. This will go like that, this will come back and be the original one. What happens if our x has an exponential? The same case we are taking it here. So if y, which is more realistic, is some sort x to the n, which will be each one of these cases here, how can we do this formula for this one? We already did it here when we have an exponent, which it will look something like this. Y will be equals to x. We know we need to add 1 if you plan to do the derivative of this. So it will be n plus 1 over n plus 1. So it's x to the power of n plus 1 over n plus 1, in case we have an exponent like this one here. Let's do that formula again. Y will be equals to x to the exponent plus 1 over n plus 1. And in this case, let's do a very simple graph, a very simple function. Our function will be where y is equals to x squared. It's not linear like the previous one. The previous one in here, remember, y is equals to x. This time we are adding a square in there. So how can we do the same when we have an exponent? We already saw how to do that, and we have the magic formula here. Let's do the graph. Without doing the coordinates, we will know the values if we simplify this. So let's have x, y. We know if the value is 0, we are doing this all the time, y will be 0. If x is 1, y will be 1. If x is 2, y will be 4. If x is 3, y will be 9, and so on and so forth. So let's do the graph. When x is 0, y is 0, so they're both at the origin. When x is 1, y is 1 as well, so it will be some point in here. When x is 2, y is 4, so it's some point in here. When x is 3, y is 9. When x is 4, let's start doing this here. This value will be 16, so it's someplace up here. Let's just do it like that. If you see this, we have a curved value that's exponentially going up. Obviously, I'm not drawing a perfect curve, but now you can see that indeed we don't have a straight line anymore. So how can we calculate this value? The area again. We're gonna choose a section and we're gonna perform the same calculations. So for one, let's start doing the same thing. We're gonna take one area and we're gonna do the calculation in there. Let's work in a zoomed out version of all this section in here. If we have a value where the curve is going, for example, like this, if we take one area, one unit area, we know if we do like a perfect division, the curve itself is not gonna be the exact half of one unit area. But let's apply the formula and figure out what values are we dealing with. We know for every value in x, y is gonna be x squared, right? So if we apply this formula to x squared in order to calculate this, we will know that's gonna be like this. X squared will be equals to x to 3, because that's n plus 1 over 3. So in this current value we have here, it will be 1 to the cube over 3, which if we deconstruct this, 1 to the cube will still be 1. Therefore, this is equal to 1/3. And this is the magic result we want. The area under the curve, this section here, without doing rectangles or anything, is 1/3 of the unit area of this square we have here as one unit area. If we go back here, now we have these values in here. So if we do that calculation, 1 divided by 3 is equals to 0.3. And we know exactly the area for this section under the curve. We will do the same in here, assuming this was correct, like this point should be here, 2 should be in here, not in this side. You have like a straight line in there, and we do this. For this next one, we just need to calculate. We do exactly the same in order to have this area, the area in here, and we just do the sum of these two. And we will do that until the point we want. Our point B, we can keep extending that. And one of the ways we can keep extending that is just to keep moving this. If we have until n, we just sum all the previous areas doing exactly the same formula, and we have officially calculated the area under a curve. Extremely important, because in the same way we saw it at the beginning, by calculating the derivative in our particle, with the derivative we know the speed on which the particle was traveling. And if we add the integral, now we know the distance as well. So we have calculated those two. The more we add into our data, the more machines can learn better. Because now we have more precise data on those two values. We can do more and more and more. Integrals will be vital in AI as well, in many different areas, but especially when we're dealing with probability models. Just to give you an example, like ChatGPT is trying to predict which one's going to be the next word in the sentence, or classification models, especially also when we're dealing with the architecture of a model itself. Once we check loss functions and optimizations, it's going to be used a lot. Also, it's going to be used a lot in neural networks, activation functions. It's going to tie in straightly on all the stuff we're doing here as well. So it's important to know all these kind of operations and when everything is coming from. Let's move on to the chain rule. Before we jump into this, let's do some practice on derivatives, so we get familiar in this. This will be very simple. In a production scenario, it can get really complicated, but as usual, we start with the basics first. So let's derive something. As a common instance, if we have something like x to the power of 2, once we derive that, we need to lower this exponent as the coefficient. So it will be equals to 2x. And this is the derivative of x to the power of 2. Let's do another exercise. If we have x to the power of 3, the rule is, first of all, we're going to do that first step. We're going to lower this exponent, so it will be 3x. But the main rule is that we need to negate 1 to this exponent. In this case, it will be 2. In the first instance, if we're squaring x, this is x of 1 because we are negating 1 to this value, but we don't write 1 as the exponent. If you leave it empty, it's going to be implicit as 1. So this will be the correct result for x3. And obviously, x to the fourth will be equals to 4x to the third, and so on. So the formula for this will be x to the power of n is equals to, when we derive this, when we do the derivative, will be nx to the exponent of n minus 1, which is everything we're doing in here. This is the very core, simple functionality of this. Just remember, if you have something like an exponent where the value is going to be 0, everything to the power of 0 will be equals to 1. So any value to the power of 0 will always be 1. Those are some common rules we need to follow. So if you do the derivative of just x, we know there's a 1 implicit in there. If we do the same rule, we're going to move the exponent as a coefficient, so it will be 1, x, if we subtract 1 will be 0, x to the power of 0 will be 1, therefore the answer of the derivative of x is 1. If you have another case like 2x to the power of 0, we'll do the same. We bring in 0 to the front, that will be x 0 minus 1 will be 0, and then obviously the answer for this will be 0 at the end, which this is telling us that the derivative of a constant will always be 0. So if we have just 2, the answer is 0. If we have 50, the derivative is 0. For any constant, just a pure constant, the derivative will always be 0. Let's keep doing more exercises. So if we have 2x, in this case, which is the opposite as this one, how we can calculate the derivative of this? Well, the derivative of any value followed by x is going to be equals to the main constant. So the derivative of this is 2. If we have 5x, the derivative will be 5. If we have 100, it's going to be 100. That's very simple to follow. Let's keep doing more complex ones. If we have something like 2x to the fifth exponent, how can we deconstruct that? This time we have a number already in front. What we need to do is still bring this guy into the front, but we're going to multiply those two values, which will be 2 times 5. And remember the rule, we need to subtract 1 from this, as we established here, which will be x to the power of 4. Which the result is 10x to the 4th. That will be the result of the derivative for this. If we have 3x squared, the result will be, we're bringing this to the front, so the result will be 6x. We are negating this one value from the exponent, which will be 1, so the result is 6x. Let's do a couple of more so we can get really familiar with this. If we have something more complex, like something like this, what's the derivative of all of this? We know the constants will be 0, right? In this case, it will be, we're bringing this to the front, we're multiplying those two, will be 6x, and we're negating 1 from this exponent, so it will be 6x squared. Let's do the same for here. We know the derivative of this will be just 6, and the derivative of a constant is 0. So this is actually the answer. Let's check more examples. Let's say now we have a composition like this, 2x squared, and we also have x to the fourth. How can we construct that? We know the rule internally that we need to move that to the front and multiply that, so the result for this will be 4x. We have to subtract 1 from here, so it's implicit, so it's just 4x. We need to multiply this by the non-derived version of the second element, which will be x to the fourth. And we need to add in here the non-derived version or the first element, which is 2x squared, times the derived version of the last element, which in this case will be 4x to the cube. And that's our answer. Let's keep checking more examples. In the case we have, for example, x over y, we need to find the derivative of this, which will be equals to, it will be the derived version or of the numerator, so we mark that as x prime, times the non-derived version of the denominator, and we're going to subtract the non-derived version of the numerator times the derived version of the denominator, which is y prime. We're going to do that over the square of the denominator, so that's y squared. That's the formula we saw before in the derivative and the one we were using so far. So let's do a practical example with this formula we have up here. If we have something like 3x squared times 2x, and we divide that by 2, how we can calculate the derivative for this? Let's use the same formula. We need the derived version of the numerator, which in this case, if we deconstruct this, we will move this to the front and subtract 1, which will be equals to 6x plus 2. We know the derived version of this is just 2. And we need to multiply that by the denominator, in this case is 2. We need to subtract that from the non-derived version of the numerator, which is all of this, 3x squared plus 2x times the derived version of the denominator. We know this is a constant, so it's going to be 0. In the formula for all of this, we need to divide this over of the denominator to the square. And that's the answer. You can check lots of problems by this. You're not going to be doing this by hand again, but it's extremely useful to know how to create the derivatives of different functions. If you have sine of x, the derivative will be cosine of x. If we have cosine of x, the derivative is negative sine of x. If you have a tangent of x, the derivative of the tangent will be 1 plus the square of the tangent of x. And you can check more resources about this. Now, we need to know this in order to do the chain rule. And the chain rule is basically when you have functions inside of functions. And you can have really complex ones and a whole chain of functions that depend on other functions, which will be, again, a function inside a function in the most simple example. And you need to do the derivative starting from the outside and going into the inside. So let's do that exercise and let's check about that. So if we have a case, let's say y is equals to 3x plus 6 to the square. In this case, just by looking at this, we can see we have an inside function, everything in here, and an outer function, which is squaring everything. So in order to solve this with the derivatives, that's when we apply the chain rule. This is a function inside another function. And remember the order. We always go outside first, and then we go inside. And we keep doing this until we don't have any functions left, or we don't have to apply the chain rule again. So for this, the result, you will see it as dy dx, or can also be seen as y prime. But basically this will be equals, we're gonna apply the same power rule. We bring in this exponent as a coefficient, which will be 2. And then we need to add all of this inside because we still haven't solved the inside part. We're just doing the outside part, which will be the same, 3x plus 6. And now we need to multiply that by resolving the inside function, the derivatives of the inside function. So we know by doing that it's gonna be 3. Because of the result, on doing the derivative of the interior part is going to be equals to 3. Let's do that really quickly. We know that the derivative of this is going to be 3, and the derivative of a constant is 0. 3 plus 0 is still 3. That's how we get this result. So in order to keep making this a bit cleaner, the next step we will do is to bring this guy to the front, which we do that by multiplying 3 times 2, that's equal to 6. And the inside part remains the same as here, and that's the actual answer. So y prime is equals to this. We are deconstructing that from the outside to the inside in order to have a successful chain rule calculation for the derivatives. Let's do another example. If you have something like h of x, which is equals to, let's do x cubed plus 2x minus 7 to the 10th power. Okay, let's do this step by step. The result will be h prime of x, and this will be equals, let's do this again. We're gonna bring this, let's start with the outside function and going inside. So for the outside, we have to bring this as a coefficient, and the inside remains the same. To the cube times 2x minus 7, and we multiply this by resolving the derivatives of the inside function. So we know for this, the derivative of this will be 3x squared. We already know we need to subtract 1, bring this to the front, plus 2 minus 0. So we don't do that. We can just keep it like this. And that's the answer. If you have something like y is equals to the sine of x squared minus 4x, if we start deconstructing this, y prime will be equals to the cosine of, remember we're doing the outside part first, so this still remains the same. By doing the outside, it's just the sine function, minus 4x, and then we need to resolve the inside function. And we will do it like this. Obviously this will be 2x minus 4. And again, this will be the answer. Now these are really simple. These are just two, one outside function and one inside function. When we see in our neural networks and the calculation we need to do, this can get really, really heavy. There can be thousands of functions inside functions. So in our cases, it might look something like this. If we have a master function like a, and inside we have b, and inside b we have c, and maybe we have d, and then in here we pass in x. Maybe outside here we have plus 1 or something else. Still, this is really tiny, and you will understand this better once we are reaching this stage, but our architectures will look really big. When we have an input, in this case, x will propagate through all these functions and do something at the end. And as you can see, all the functions from the inside to the outside and vice versa, it will depend on x. So what happens if we nudge the value of x? If we change it by h a little bit, how d is going to change, how c is going to change, or b, or the very beginning, which will be in an input stage. So once we reach this value of x at the end, we will have some result. If we need to tweak that result, if you need to modify it to make it go larger or smaller in value, we will have to calculate the chain rule to check every single state on the function of how x, the final result of x, was created. That's why it's extremely important to know the chain rule. Obviously, we will do derivatives for every single stage, and we will do it backwards and forwards for our needs. Linear algebra. This will be a high-level overview again, and it will depend up to you if you're gonna go deeper, but the basic core concepts will remain the same. let's start talking about vectors. So vectors are one-dimensional arrays of numbers. And you Houdini users will be familiar with this. And lots of the math we're gonna use in AI, you're probably familiar with some of these core fundamental mathematical operations, because you've been using so far dot products, cross products, and so on. We are basically checking the same. Now, again, vectors will be one-dimensional arrays. And the characteristics of a vector, we can split that in two ways. They will have a magnitude or a length and a direction. You probably, if you mess around with velocity fields, effect simulations, and all of that, you're really familiar with this. But basically, we have some numbers. It's an array, it's a container with one dimension. So if you have, for example, a vector like this, where you go into negative values and positive values, you can interpret this as the coordinate of the data entry, the location of these values, which basically says to the right you have a value of -2 and down 4, and you can transform the data entries based on this. You will see vectors in different representations. For us, we're gonna keep it like this. Sometimes you see them vertically, like this. It's a simple array, but we are based on this as our core structure is gonna drive more complex structures like matrices down the chain. Now, each one of the values inside a vector, for us in AI, we're gonna denominate those as samples, okay? Really simple. So let's do some coordinates here, and we have some values. So if we say in the direction of a vector, let's say we have a data point here. This is X, this is Y. If you have some data point in here, the concept of doing scalar operations in a vector, and the scalar is another of those terminologies, is how are we going to move this point in our coordinate system. Remember, we can have more on this side. We can go into negatives on each axis. So let's say we're gonna move this point with a vector coordinate. We can say move this point to the left. And again, since we have negatives here as well, if we move this 1 unit, will be 0, it will be here. And then we can say, and then move 2 units up, which will be here. So the point now will land in this location. And we have these values that we need to know, which will be the length or magnitude and the direction, which the length basically is from here to here, and the direction we know is this one. We have those properties in order to do all calculations. Again, to reiterate, a vector will be one-dimensional arrays. If we're dealing with multiple dimensions, that will become a matrix. Really simple. And we can talk about scalar operations in the vector. So a scalar basically means an operation that involves a vector and a number. So if we have a vector like this, 1, 2, 3, let's do that again down here. And we just add one value to this, plus 1. This is a scalar operation, really simple. The answer will be to add 1 to each one of these. So the new vector will be 2, 3, and 4. That will be a scalar operation. We can also do something called an element-wise operations. Let's do a new space here. It's easier to denote this in vertical context. So if we have a value a1, a2, this is one-dimensional, it's a vector, and we add another vector, b1, b2, the result for this in an element-wise operation will be a1 plus b1, a2 plus b2. So this is element-wise operations. You can see we are adding every element of each array. Another kind of operations in vectors, let's do more space here, will be the dot product, which you should be familiar with this already. So basically the dot product of two vectors will be a scalar. Keep in mind, really important, dot product is one of the main mathematical operations we will do in our entire processes, which later we will see about matrix multiplications. In order to do that, we do it with a dot product. In this case, if we have, let's do the same, a1, a2 times, we're doing a product now, b1, b2. The result of this is a scalar, which will be a1 times b1 plus a2 times b2. If you notice, we are doing the multiplication with these elements, and we're adding to the multiplication of these two elements. These are really simple in one-dimensional vectors, and we will see about matrices how to do the dot product in a second, but this is called the dot product. Another operation is called the Hadamard product, which is basically if we do the same a1, a2, one-dimensional vector, and we multiply this by b1, B2, another one-dimensional vector. The result of this will be a new vector with these elements, which will be A1 times B1, A2 times B2, and this is called the Hadamard product. Now, it will be a lot to draw here, but you can investigate more about something called the vector fields. If you have a bunch of data points, which we are dealing with a more complex vector in this case, if you're applying vector operations to all of these, how are they basically moving? If you're changing the direction for this one, maybe it's going there, maybe this one is pointing to this other one here, and this one to this other one, you will see like this flow, this field of movement. How are you altering the positions, magnitudes, and doing all the operations, dot products, and basically changing this? As you can see, you are creating a field, which is a representation on all these points. How are you mutating them in terms of magnitude or length, and in which direction are you moving these different data points? Let's talk about one of the most important concepts for us, which will be matrices. So if you're dealing with a vector of 2 or more dimensions, that will be a matrix, which I usually interpret as this. You have some values. Matrices are conformed by rows and columns. So you always start horizontally and then vertically. If you count this will be 1, 2, 3 rows and 2 columns. Therefore, we can say this matrix is a matrix of 3 by 2. Extremely important to know the shape of the matrix. This will be vital for you down the chain. And most of the issues you have as a beginner in AI will be because you're dealing with different shapes when we're supposed to use a uniform shape with your different matrices. So knowing the shape is extremely vital at the beginning. So in the same concept as vectors, how can we do, for example, some operations in a matrix? Let's do the most basic one, a scalar operation. Let's create another matrix, a really simple one. You already know if you're doing a scalar operation, it's just mutating this by adding one number. So if we add this plus 1, the result will be a new matrix with the new values. So that's 2, 2, 2, 3, 3, and 3. This is a scalar operation in a matrix. Same case, let's do element-wise operations. We have A, B, C, D, 2 by 2 matrix, plus, let's do 1, 2, 3, 4. The result is element-wise will be A plus 1, B plus 2, C plus 3, and D plus 4. So we have A plus 1, B plus 2, C plus 3, and D plus 4. This is element-wise operations. Let's do a Hadamard operation in a matrix. Let's have, again, A1, A2, A3, A4 times another matrix, B1, B2, B3, and B4. Notice they are the same shape. They are both 2 by 2. So the result for this will be A1 times B1, A3 times B3. The other elements will be A2 times B2 and A4 times B4. Again, doing the same operations, A1 times B1, which is this, A2 times B2, which is this, A3 times B3, which is this, and A4 times B4, which is this element here. This is a Hadamard product. Really simple operations, especially easier when we're dealing with just scalar operations or with matrices of the same shapes. So let's talk about another fundamental operation you need to know, which I can guarantee you will doing a lot, and that's transposing a matrix. So if you have a matrix like this, transposing a matrix means we're going to swap the columns by the rows. So we're going to invert this matrix. So if the shape of this is 4 by 2, the result will be a new matrix with a shape 2 by 4. In order to do that, we are swapping the columns with the rows, or vice versa. So notice here, this is one column, this is another column. So the first column will become the first row, which will be A, C, E, G, and the second row will be B, D, F, H. And now the result of this is a 2 by 4 matrix. I can guarantee you again, you will be transposing matrices a lot. in your career. We will do operations about all of this in code. For now, it's just me showing you the high-level overview concept. Now that we have this in mind, let's talk about the most important concept, which is matrix multiplication. So with matrix multiplication, we need some rules in order to make it work. Matrix multiplication relies on the dot product to apply this to different combinations of rows and columns. And the main rule, the first rule we need to follow is the number of columns of the first matrix has to be equal to the number of rows of the second matrix. That's the number one rule. So let's call this matrix A. AC for matrix A columns must be equals to the second matrix, so the number of rows in the second matrix. And the second rule is about the shape and the result size of that operation. So if you have a matrix that's m times n, and then you have another matrix which is n times k, the result will be an m times k matrix. So we will see that in practice. Let's do it first with the same size, the same dimensions, and the same shape of two matrices. And again, we will rely on the dot product to do this. So let's have a matrix like this. The result for this will be A1, if this is matrix A, and this is matrix B, will be A1 times B1, A1 times B2, A2 times B1, and A2 times B2. So let's check what's happening here. This row will be A1, and this row is A2. For B, this column is B1, and this other column is B2. So A1, B1 means we are taking the dot product of the first row in matrix A and the first column in matrix B. The next element will be A1 again times the second column of B2, which is this one here, and so on. So let's make a more clear example. Let's do a matrix here. What happens if we try to multiply with a matrix of the same dimensions, A and B? We need to multiply all of these values to all the values in the columns for matrix B. Notice we have of length 3, and in here we have of length 2 vertically. Therefore, we can't do this operation, because if you multiply this one times this one, and then this one times this one, there's no room for the last element, which is 5. So there's not another row in there. Therefore, this rule doesn't comply with the rules we need for matrix multiplication. So what's the solution for this? We need to transpose this matrix B. So let's do that. Let me do the same matrix down here. And now let's work with the transposed version of matrix B, which will be 1, 6, 3, 1, and 1, 2. Now we can perform a matrix multiplication. So let's check the shapes. This is 2 by 3 for matrix A, and matrix B is 3 by 2. The rules is these inner dimensions here has to be the same. Otherwise, we can't perform a matrix multiplication. So that's the first check we do. And the second part of this is the result matrix of this multiplication will be this shape of the outer elements in the matrices for the shapes. So we always need to follow that convention, otherwise we can't do a proper matrix multiplication. That's why it's important that sometimes we need to transpose matrices or do some kind of modifications in order for us to actually comply to those rules and be able to perform the operation itself. So let's do this operation. The result we're going to have here, I'll do the operations first and then we will build the matrix. So let's do it a little bit up here. What we're doing is multiplying the rows times the columns. So we're going to start with this row and with this column here. So the result of those, if you go element each one of those doing the dot product, will be 2 times 1 plus, we need to add all of these operations, 4 times 3 plus 5 times 1. And let's check those. So 2 times 1, this one times this one, 4 times 3, this one times this one, and 5 times 1, this one times this one. If you add them all, it will be 19. Let's do it for the next operation. Since we still have columns left, we still remain in the same row. So the next operations will be 2 times 6 plus 4 times 1 plus 5 times 2. Again, this one times this one times this one, and this one times this one. The result of this will be 26. Let's move to the next one. Since we don't have any columns left, we need to go back to the next row, which will be this one down here. 1 times 1 plus 6 times 3 plus 2 times 1. 1 plus 1, 6 times 3, and 2 plus 1, which will be equals to 21. And the last one we will do is 1 times 6 plus 6 times 1 plus 2 times 2. So 1 times 6, 6 times 1 plus 2 times 2. And the result of this will be 16. So our result matrix will be in this shape of these values here. Will be 19, 26, 21, and 16. Notice the shape. As we said before, the shape of the resulting matrix during those dot products will be on the outer elements of the shapes. So it's a 2 by 2 matrix. Really fundamental, one of the more core basic operations you do for most things in machine learning. And we will see once we reach this stage again in our architectures. You're not going to be doing this by hand, but there is a lot in matrix multiplications. And we will do some examples in code. Keep in mind, these are really simple matrices, but in the production, in real life data, this will be massive and possible with lots of dimensions. Hello. So let's do some examples about these linear algebra concepts, but we will do it in a Jupyter Notebook. For now, we're going to use NumPy. We will see about NumPy and a Python refresher on next week, but we're going to use it nonetheless for now, just so we can do some basic operations. By all means, you can do this without NumPy, but I want you to get used to using NumPy from now on because it will be the correct and more efficient way of doing all kind of mathematical operations. Usually, we're going to start by importing NumPy as np, and we're just going to use this library for now. So let's do element-wise operations in 2 vectors. Start with a simple one. Let's call this one x, and it's going to be equals to np.array, and let's pass in an array. Let's do 2, 4, 5, and y will be equals to numpy array, and you're going to pass in 4, 2, 6. Very simple. Let's do some scalars with this. So y plus x is going to be that array. This is element-wise operations in those 2 vectors. We can also do y minus x, and we can also do, for example, y divided by x. And these are the results we have. Again, element-wise operations, really simple. They are different arrays, but with the same shape. Now let's do the dot product. Let's have 2 arrays again. Conveniently, we have a function to the dot product. We will do a manual approach to a matrix multiplication and transpose a little bit later, but for now let's just use numpy. Again, we will see in depth about numpy later, but for now we can just do numpy.dot for dot product, and we pass in the matrices. And the result is that one, 59, for the dot product of those 2 vectors. Still in the basics, if we want to do a Hadamard product, we can pass 2 vectors as well. So if you want to do the Hadamard approach, that will be multiplying y times x, and the result will be a vector. Always remember, the result of a dot product will be a scalar, and the result of a Hadamard approach will be a vector. That's basically the main difference. Okay, let's start doing some matrix multiplication. I'll just do some space here, and let's start working with this. We already saw the logic on how to do this, and we're going to implement this in Python. We're going to do it with raw Python at the beginning without using any library. So let's have 2 matrices. We'll do the same ones we did in our example. So those will be, if we establish this matrix as 2, 4, 5, it will be a 2-dimensional matrix, and the other numbers were 1, 6, and 2. So this is matrix A, and now matrix B will be equals to 1 and 6, 3 and 1, and 1 and 2. We have matrix A and matrix B, the same ones we did manually in the previous example. So now we're gonna define a function to do this multiplication. Let's call this one matrix mult for matrix multiplication. We're gonna take in a matrix A and some matrix B, which it happens we already created those, but we can pass any matrices in here. Now, the first thing we need to do is, remember the rules, we need to check for the shapes. If the length of matrix A in the first element, which if we check this first element of matrix A, this will be of length 3. If that one is not equals to the length of matrix B, let's check the length. If we're checking just one of the elements inside matrix A, that will be this first element here. And if we're checking the length for the whole matrix B, it will be the number of rows, which has to be the same in this case, is 1, 2, and 3. This is telling me the shapes will be compatible for the matrix multiplication. So we're doing the check. If that's not the case, then we can just raise a value error. So for this case, it will raise that error and we cannot perform this. Once we raise that, we can also return something, or we can just leave it like that. We will need a new matrix in order to add all the elements as we are performing this dot product. So let's call that one result. And it's gonna start as empty. We will keep adding into this as we do the operations. So now we need to traverse. We're gonna traverse in the rows of the first matrix first. So for row in range, the length of matrix A, in here, for each one of these, we will need a new row because these are two-dimensional matrices. Result is the main outside container, and for each one of these, as you can see here, we need another list, another array. So what we're doing here is, for each one of those, we will have a new row. Let's call this one new row. It's going to be an empty array. And now we need to traverse the columns of the second matrix. So for call in range, this will be the length of matrix B, but we are checking the length of each one of those elements, which obviously they has to be the same. Which at this point we will have the columns and the rows. Again, to reiterate, for the first rows, we are checking each one of the rows in matrix A. And in this case, our range is going from here to here. So we're doing the columns. That's why we have the range, the length of matrix B, and we can pick any of these elements. As a standard, we will pick 0, the same way we did it here. They're all the same size. So it's gonna work like this. Now that we are in there, we have a reference for each one of those elements. We will need to do the dot product. So let's call this one dot product. It's gonna be equals. Remember, we're doing all of those multiplications. Rows by the columns. Rows of matrix A by the columns of matrix B. But we need to sum them all. You remember the formula? You can go back to the previous videos if you forgot or you need a reminder. But in Python conveniently, we can just do the sum of a container. In this will be matrix A. We're gonna iterate through this. So each one of those elements, we're gonna specify it as K. It can be any number, any name for that variable. But for now, we know we are in the row and we're trying to grab that element, which we're gonna denominate that as K. So we're gonna multiply that by matrix B. And we're trying to grab K, which will be that element, but this time in the column. For K in range, which will be the length of matrix B. So we're basically doing that same operation I show you manually, but now we're iterating through the rows and the columns, and we're doing that multiplication for each one of those elements. Since we need the sum at the end, that's why all of this is wrapped in the sum method. Now we have that value for that dot product, which we will need to append this to each one of the newly created rows. So new row that append the dot product. Now that we have that, we have individual rows, and we need to append this to the main container, which is result. So in this level, we're gonna append to result, which will append the new row. So for each one of these, now we have the correct matrix in the correct dimensions. At the end, we're just gonna return the final result, and that's pretty much it. Oh, I have a typo there. This is 4, not 4. I hope you catch that. I'll probably do lots of typos, but it's okay. There we go, we have our function. You can review the code again, go back to the previous video and check the operations that we are doing here. You can deconstruct this if it's confusing, but basically K will be each element we're currently landing on for each one of these, and we're gonna do that multiplications of rows times the column. We need to sum them all, and then that value is our dot product. The dot product we will append to each new row we are creating, and those new rows will be appended to the final container, which is the main matrix. Now that we're here, we can test this. So let's call variable res for result. We're gonna call in that function, and we're gonna pass in our matrix A and matrix B. And indeed, it's exactly the same matrix we got at the end when we did it manually. So this one works. That's how we're defining the multiplication of two matrices. So what happens if indeed the shapes are incorrect? We're gonna do a manual approach of a matrix transpose. So let's do this one on Markdown, and let's check the logic for this. Let's have just one matrix. We already have matrix A. Let's just remind ourselves how matrix A is looking, and our job will be to transpose this. So let's create another function. Let's call this one matrix or transpose matrix. We will need some matrix. Let's just pass M, and we need some result. So we can call this one TM for transpose matrix. Let's just do the same similar range we did before. We're gonna loop through the rows and columns. So in this case, we're gonna swap the columns by the rows. So we're gonna just take the length of each one of those elements. So we can take the length of the element 0 inside this two-dimensional matrix, which we will do a range. So for I in range, this will be the length of M and the first element, which will give us the columns. We will need again a new row for the result. So for J in range, the length of the whole matrix. Now for the new row, we're gonna append M of J I. So basically we are swapping. Instead of going in this order first, we're appending those elements in here. After we have that, we're just gonna append to our main transpose matrix that new row. At the end, we're just gonna return the transpose matrix. So let's check this one. We know how matrix A looks, and now we're gonna transpose that. And there we go. You can see each element is transposed. Now it's 2, 1, 4, 6, and 5, and 2. Okay, now that we understand those operations, let's start talking about some concepts. Now, right from now, I want you to think this way pretty much through this entire course and your career in general. We need to think about efficiency as well. We can split the whole field of AI in two parts. One side will be the architectures, and the other side is efficiency. One cannot work without the other, and they work interchangeably. Efficiency will be key. Efficiency is obviously one of the main aspects in software development in general, in technology in general. You name it, everywhere, game development, whatever field you want to choose, efficiency will be one of the main topics you need to tackle at some point. Because your algorithms, your development needs to be efficient in order to work in increased performance. As we see, one of the main things we're going to be doing as AI developers will be experiments. Experiments will be all over the place in many different shapes, in many different fields. So in order to have more experiments, in order to develop more experiments, you need to have better efficiency. There will be some nuances and new ways efficiency is being driven by new technologies, like if you check some new papers. And we will see about quantization way later, but for now, just keep in mind, even if you do some kind of development, that's going to save you microseconds or nanoseconds, that counts a lot because you need to be able to do scalable operations and scalable programs or models. The data you handle in the wild is huge. We're talking about massive amount of data and calculations. The more you save your computer and doing these kind of operations, the better you become as a developer in general, especially AI. So in this case, we're doing some matrix multiplications, we're doing some operations here and there, and we will check different libraries just for efficiency as well. Like just by using NumPy, you're already making some efficiency in your pipeline. But besides all of that, you need to be able to do better algorithms in terms of efficiency, in terms of how you're using your computer resources. In the wild, again, we will be dealing with huge matrices. And there will be a lot of cases that you have zero values in these matrices. As you can imagine, obviously I have two examples of tiny matrices here, MA for matrix A and MV for matrix B. But you have a bunch of zeros in there. In the case, a whole column will be full of zeros, or a whole row can be full of zeros. You know that multiplying any number by 0 is going to be 0. So if you're actually using these values, you're wasting resources. These are called sparse matrices, where you have a bunch of zeros in there that are not going to do anything. Sometimes you want to use those zeros or negative values, but in this case, we are multiplying matrices, and they will be useless to have those operations in here. So how can we tackle when we are facing sparse matrices? For example, this matrix here has lots of 0 possible values. And this is just one example. There are many answers in text fields and whatever you want that you will have lots of sparse matrices. There are many ways of dealing with this. I'm not just showing you the only way of doing this, but you need to know how to handle these scenarios and not waste lots of computing resources in this. This will be useful for some development for a program we will do next week when we're dealing with the maze solver program. But in this case, let's take on the logic for this. We know we're not going to use the 0 values in the matrix. All the scalars in there will be useless for our needs. So in these samples, in all these values we have in these matrices, basically we need to fish around for the actual useful values we need in here. So if we start traversing these matrices, we will have some coordinate system for rows and columns, right? For example, let's just take the first row here. We know that will be row 0. And if we start navigating here, we can see there is a value in there that is not 0, which will be in the first column. So the coordinates for this one will be 0 and 1. For example, for row 0 and the element is 1, we know that value, that those specific coordinates in our matrix is one value we can actually use. If we start doing the same, let's say we'll end up in this one. That will be row 0, 1, 2, that's row 2 and column 1. So we need to fish around in our matrices for these values we can use. We're going to create a function and we're going to create a helper function to help us find those values. And we will use this helper function inside the main function in order to perform this efficiently. So let's start doing this. Let's define the main function first. Let's call this one sparse, for sparse matrix multiplication. We're gonna pass in matrix A, matrix B again. And since this is a matrix multiplication indeed, we always need to perform the main check. We need to check the shapes of each one of the matrices in order for compatibility. So if the length of matrix A at 0, you can do it either way, is not equal to the length of matrix B, right? We know this is not valid. We can either raise an error or just return like an empty matrix or something, or -1, it depends. So in this case, we will have two sparse matrices and we will work in this helper function in 1 second. But for now, let's just call this one S of A. So the sparse matrix A will be equals to, let's call this one get useful values. Obviously this is not a good name, but you get the point. We need to pass matrix E, basically all non-zero values in the shape of a dictionary. That's really important because we need to traverse through the keys and value pairs. In this case, the key will be those coordinates I was talking about. Let's say for this, the key for this element will be 0, 1 for row 0, column 1, and the value for that key, it will be the value itself in the matrix. So that's for A. We will do the same for B. Since we have those sparse matrices, by calling in that, we will create in a second that getUsefulValues function, we will have a new matrix. So matrix C will be equals to, let's do a range here, 0 times the length of matrix B for any variable in the range of the length of matrix A. We are creating a matrix full of zeros in the shape of the resulting matrix. Remember how we calculate which shape the resulting matrix will be. We'll do exactly the same, but we have a new container full with zeros. As we traverse through the keys, we're gonna fill in this container with the proper values. Remember, all of this will be really handy once we check the maze solver next week. And you can come back to this video to check it again. But basically now we have that container, which is a new matrix, the resulting matrix full of zeros with the shape we want. So now we'll do the traversal for the keys. For I, k in the sparse of A, that keys, we need to fetch for the keys. We do an inner loop. So for each one of those values, for j in range, that will be the length of matrix B. Since we're dealing with the columns, we will check the size of any of those elements. Now that we have that, we need to perform the check. So if k and j are in the sparse matrix of B in the keys, and let's call this one sparse of B. So if these values are in the keys we're trying to find, then we perform that multiplication. So we're gonna fill in the values for matrix C. So that will be matrix C of I and j plus equals sparse of A, I and k, times the sparse of B, k and j. At the end, we're just gonna return matrix C. So let's do the helper function and then come back to this one to make it clear. So let's define this one, get useful values, and we need to pass in a matrix, right? So the final dictionary, let's call this one res for result, will be the return value we want. So we're going to start with an empty hash table or dictionary in Python, and let's do a range in order to fish around for the values that are non-zero. So for I in range, the length of the matrix. For j in range, we know the drill by now, length of the matrix of any element, which will be the columns. So if matrix I, j, so if matrix row column, the current value we landed on, is not equals to 0, then we're gonna append to this. So the key for this will be I, j, it's gonna be equals to the matrix, so that value. And then we're just gonna return that dictionary. So now that we have a grasp for that, we just have a key value pair that's gonna look something like this. Let me do some space here. Let's make sure we have everything visible. In the case for matrix A, will be some sort of dictionary like this. We know the key is gonna be in this shape and with the coordinates, which will be row 0, column 1, and the value is the value itself. So we're doing this for every value we find. And that's basically the return form of our dictionary. The loop we're doing here is we add 2 of those sparse matrices by calling in these functions on each incoming matrix into the main function. So we are indeed looping through the keys, through these values, and just basically comparing that. If those values are in matrix B, so we're looping through the keys as well, we are performing that multiplication. Therefore, we are just replacing those values. We have the shape we want at the end. And if the values are 0, we're never doing that calculation and they will remain 0. That's why we're filling in the original result matrix full of zeros. So let me kill all of this. Oh, this should be obviously that element. So it was a typo there. Hope you catch that. Get used to typos. I will probably do a lot throughout this course. But now let's test this one out. So let's call in a variable result. Let's call in the sparse matrix and we're gonna pass in MA and MB, and we can just execute this one. There we go. And obviously these are not too good matrices because they are landed in 0, so the value is going to be 0 for the multiplication. Let's create new ones. So let's call this one A, and let's do just a small one. It's going to be two-dimensional as well, 0, 2, 0, and let's do 0, 0, 0. Let's do another one here. Let's do this time, it has to be 3 by 2. So this one is 0, let's do 0, 1, 2, 0, and 1, 0. And there we go. Now this is more clear on what it's supposed to do. We're not wasting lots of resources. These were bad examples, but you get the point. The shape is correct at the end. The inner shapes, outer shapes, and remember the rules we are creating, and this will be the correct value. We're never touching all the 0 values, and now you can scale these operations to big matrices. Okay, so let's start talking about data itself. Data will be one of the main components of every program, and we're not just talking about the data we find around, like images, text, all of that. All the possible data you have in a program and the data structures and different ways you will interact with your own applications and development. So let's start with data. First of all, it's a habit and it's typical in people to assume things visually, and that's not how computer works. So we really need to start being comfortable in the mindset we need to take for development technologies. All the stuff you see here, Kaggle, different data sets, or whatever image you can find, or videos, or text, or audio, whatever you want, we need to transform that into numbers at the end. Everything you see in your monitor, every data, everything you see in order to create a program is nothing but zeros and ones at the end. It doesn't matter if it's an image, if it's text, if it's audio, is whatever you want. We need to start getting into the mindset that everything is just numbers at the end. All right. So the different kind of data we're gonna be talking about and dealing with, you're gonna see how to transform properly all of them. But for now, we know we have a bunch of different types of data, regardless of the input. Like any kind of this will be a tabular data set, relational data sets. For example, when you see columns and rows, or you have images and whatnot. So let's take a little step back and we will see mainly about computer architectures. So regardless of the input, the logic is the same. The data you will have is some numbers, some array of information in your machine. If you have everything in a cloud service or your hard drive or whatever kind of storage you're using, it will be that something where you have all your different types of data, right? When we are executing a program, we are effectively selecting components, physical components in your machine, and we are working with them. I know lots of you already know all of this, but we need to level up everyone, in case you're not very familiar with this. If this is everything in your hard drive, in your storage, can be, again, SSD, cloud services, whatever it is, this is where you have your structure. It will be a sequence of machine code of zeros and ones, switching on and off transistors in your machine, right? But in order to actually work with the data you have, all of these will be allocated in a temporary container, which is your RAM. This is the memory in your machine. RAM will have lots of addresses and all the different components you should be familiar with, because effectively it's one of the main hardware components in your computer, right? The way this is happening is your CPU is using a bunch of registers, processes, is doing this in cycles and all of that, but it is indeed dictating those instructions. So it's dictating, okay, you have some data in your drive, when I use it in the program, therefore allocate and do this round trip. So the CPU is in charge of doing those processes. Let's say in here you have some images and you're working with that. An image will be just a grid of numbers again. In order to open that image, you will borrow the locations from the hard drive and you will temporarily storage that in RAM. So you're doing some allocations in here in order for this to work. We're just gonna check later a quick overview on what's happening in stack, heap, and in the code section of your RAM. But for now, you have to be familiar on this process. So what's happening here is, in order to work with the data we're grabbing from your storage, the program itself needs to structure this in RAM. So if you have RAM like this, RAM is architecture in some different ways. You have something called stack, heap, and the code section, but again, we will check that a little bit later in a program. Mainly, you need to know there's a process of organizing your data. And in your program, let's say you also have your program in disk, your Python code or C++ or whatever program it is that is working with this data. Let's say maybe you are arranging your data, can be just the numbers in an array. So you have an array, and then you have your values in the array. All of this needs to be structured by the CPU, by the architecture of the program itself, needs to be structured in RAM. That's why they are called data structures. So there's a way to structure an array. Maybe in your program, you're adding your images or text or whatever in a hash table, right? Keys and value pairs. The CPU will have another way of organizing this and having this in your memory. Maybe you are using different kind of data structures for different things. All of these will have a process, and the CPU has to work and allocate all of these containers and different kind of types of data types in your RAM. That way you can work and you can execute the program as you need. So it has to structure the data, and there's a process for that. Efficiency will be key for everything we'll do. And that's why these are called data structures. It has to be structured in RAM in a certain way. You will have memory addresses and whatnot. So these are data structures. Another type of data, which is the one similar as you saw here, will be this kind of data sets. This is called a database. So a database is already structured for you. So the CPU, the program itself, all the logic, all these cycles happening here, don't have to restructure this kind of data in memory because the data is already structured for you. As you can see here, you have rows and columns, and you can fetch this as you need to traverse. So that kind of data is also stored in your drive, but it's a more direct approach because it's already structured for you, and then you just have to allocate that in RAM. It's still something happening. It's not like completely just using it one by one. There's still some processes happening in the background. This is a high-level overview. There's so many things and mathematical pointer algorithms and many stuff happening in the background, but this is a quick overview. So since this kind of data, the database, is already structured, it is a little bit more efficient because it's not so much of a round trip of organizing this data and structuring in memory. It will have some allocations in RAM and stuff like that, but it's a bit more efficient. That's why we use it a lot in data science, in machine learning in general. That's called a database. Now, let's take one of these, which again is one similar like this. It's a relational data set. If you have some of these and you are working with this right now in your company, and the current development you're doing is reading this specific data set and doing your development in here, that will be an operational data set. It's the one you're currently using right now. For example, let's say you're analyzing your sales in the current week or current day or current month, and you're working with this at the moment. So all the company, all the development is happening in this specific file. This one is obviously going into RAM, and you're doing your program based on this structure here. And then time passes by, and then you need to do a program because maybe this development are you doing for the sales in a monthly basis. So this one right now will go into the storage in the server in your company. Let's say you have a big storage data center where you're storing this right now. So maybe the next one in the queue, which is another data set, another database like this one here, it becomes the operational database now, because this will be considered old at this point, this one up here. So you're working with this one, and this will keep happening from time to time to time, maybe in decades and whatnot. As you can imagine, you will have lots of this in your server. It will be a bad practice for a company to not have it like this, because what happens if you need to analyze the sales for like 10 years ago or something like that? So this process of storing your databases, it's called as data warehouse. And in order to fetch this, there are lots of different algorithms. This process of fetching in the data warehouse, it's called as mining. Sounds familiar, right? Mining is something you'll probably be doing a lot, looking back in time in your data centers to analyze and query all data. And you keep doing that, keep sending it into the data warehouse and keep mining in order to fetch the info. So those are the kinds of data we are dealing with. In a very quick overview on the logic for this, we will check about big data and BigQuery later. But for now, since we're starting with small experiments and small levels of explanation, I just want you to keep in mind this is happening. So as a final quick overview in computer architectures, let me do a clean version of this. If you have some sort of image, it will be a two-dimensional matrix with a bunch of numbers, your pixel values. These pixel values will be numeric values. You need to be aware what's happening in RAM when you're using these kind of data structures. It will depend on the compiler you're using and the OS, but as a standard in modern architectures, one integer will be 4 bytes. There's also other compilers where this can be 2 bytes, but as a standard, even if you're using a 64-bit architecture, an integer by default, and I'm assuming is a common compiler, will be 4 bytes. That's equals to 32 bits. So if we're dealing with pointers or long integers, that will be 64 bits. The more you use the bits, the more precision you will have as you start dealing with data. As we will see later, sometimes you don't need to use this or this because it's too overkill. There are a lot of techniques we're going to see later about mixed precision, quantization, and all of that. But you also need to be aware that we also can use 8-bit integers, not just integers. We can also use floats, 16-bit floats. Sometimes we can use 32-bit floats or 64-bit floats. It will depend a lot in the data and the type of models and architectures we need to deal with. But you need to be aware of this. In RAM, in your memory, let's say we just take in one number, the number 5. 5 in binary will be 1, 0, 1, 0, and padded with zeros. So that will be 4, 5, 6, 7, and 8. Why 8? In RAM, each one of these will be a bit, each one of these numbers. The collection of 8 bits will be 1 byte. Since we're dealing with this, by default in your compiler, the way this is going to work is you will have more allocation in memory. This will be padded with 8 zeros because we need 32 bits or 4 bytes. It can be overkill. This is already a lot in memory, as you can see. It's a big location. Even more if you're using 64 bits, you will have more and more allocations in this direction, and so on. That's why we need to be familiar with different kind of bit architecture. Sometimes we will switch in just by using 8 or 16, and sometimes we will interchange between 8, 16, 32, and 64 bits. This is just by having one numeric value in memory. Now imagine for the whole image if it's a super big resolution. Everything we're going to be transforming in numbers. If you have a long text, an entire book would also be transformed in numeric values, float, integers, and so on. So just be aware of that, and we will see a little bit more about computer architecture as we advance. Okay, to finish this week, let's check bitwise operators. So now that we know about computer architecture a little bit more, and how the bits are working in our RAM, it will become essential to know how to deal with bits. And the operations we can have on bits will be AND, OR, XOR, and NOT. We're not going to cover NOT, but we're just going to check it really quickly. So the way this is going to work, let's have a binary number here. If you don't know about the binary system, I'll just quickly explain that. We're going to start with a graph and a count with a base of 2. We start from the right. So we have 1, and then we have 2, 4, 8, 16, 32, 64, and so on. Now in computers, we're always going to take of base 2. The numbers we use in real math and in real life, they are decimal base. But obviously we work in computers with a binary system for the reason of the transistors and the way electronics work in hardware. So if you have something like this range of base 2, and that's why everything in computer again is on base 2. So if we're doing logarithms on all of the operations we're doing, will always be base 2. So let's do a number. Let's say, for example, we're trying to do the number 19 in binary. The way we're going to do this, taking account these numbers, is first of all, we're going to place it in a way that's going to be the less than the actual value. So what I mean by that is if you take 19 and we try to place it here, 32 is already bigger, is greater than 19. So we cannot place it there. And we know from here to all the remainders, we can't place them there. Practically speaking, in our computer architectures, if we're using just 1 byte, which will be 8 bits, we will have that limitation as well. So all the numbers going to the left will be 0. We denominate that as 0 and b. And then we start counting the numbers we actually want in here. Obviously, if we place it here, we're trying to fetch 19. 16 is less than 19. So we're going to count this as 1. And we're going to toggle 1. Basically, we're going to turn the transistor on. And again, this will be 0, 0. So all this side we're going to denominate as 0b. And then we start adding this. 16 plus 8. We know the value is going to be greater than 19. Therefore, we are overshooting. We are overpassing this value. And we're going to mark that as 0. So we're going to turn off the transistor. If we add the previous value, since this one is not counting because the number is greater, we're still in this value. If you add 16 times 4, that will be 20. And it's the same case. It's greater than 19. So we're not turning on that transistor. Let's take the same. 16 plus 2 is 18, which is less than 19. Therefore, we are activating that transistor. So we mark that as 1. At this point, we have the sum of 18 once we reach number 2. So if we keep going in that direction, 18 plus 1 is not greater than 19. Therefore, we toggle the transistor on, and this is the result. 19 in binary will be 0b, 1, 0, 0, 1, 1. In computers, we will establish OB or 0b, whatever you want to call it. So let's do one more exercise. Some random number. Let's do 22. We're going to place it. It's still going to be in the same place. We're going to start at 16 because if we place it in 32, it's going to be bigger, right? So let's do it for here and down here. You're going to place the transistor here. We're going to toggle this one on. Let's add that. 16 plus 8 is 24. That's greater than 22. So we switch that one off. 16 plus 4 is 20, which is less than 22. So we're going to toggle this one on. At this point, we have 20 as our sum. I'm going to keep doing the sum here. Let's do that. 20 plus 2 is 22, which is equals or less. Therefore, this is valid. And since we already reached 22, we know if we add the remainder 1, it's going to be greater than. So we're going to toggle that one off. Therefore, 22 in binary will be 1, 0, 1, 1, 0. And that's how the binary system works. Now that we have that in mind, how the system works, let's check these operators in here. So let's do some random binary number. When we have any of these operators, bitwise operators, we're going to do operations on each individual bit. So each one of these. And usually we're going to compare that with another set of bits. So if we have another set here, let's do, for example, something like this. The way we're going to compare this, we're going to follow some rules. So the AND operator, which in Python will be this operator here, let's actually place it on top of each one of these. So the AND operator is this one. The condition of the result being 1 will only apply when you have 2 1s. So what I mean by that is, let's check these two. 1 and 0, they are different. Therefore, the result, if we do an AND operation with these two binary numbers, binary sequences, 1 and 0 will be equals to 0. 0 in 1 is again 0. Only if they are both 1, this condition will become true and the result of the AND operator will be 1. So again, 0 and 1 is 0. Now we have 2 1s. It's going to be 1. 0 and 0 is 0. 1 and 1 is 1. And this will be 0. So the result of doing the AND operation will be this one. Remember the condition. Only when both numbers are 1, the result is 1. Now let's check the OR operator. The OR is just the pipe character in your keyboard. And let's do the same here. For the OR operator is sort of the opposite, but not exactly the opposite. Only when the two numbers are 0, the result is 0. So in this case, if we're doing the OR operator in these two values, the result will be 1 because they are different. This is 1 again, 1, 1, and only when they're both 0, the result is 0. And so the result is all of them being 1 if you're using the OR operator. Now XOR, the XOR operator, which is the caret symbol or the hat symbol, will work in this way. If they are both the same number, the result will be 0. So in this case, the result here is 1. The result here is 1, 1. Because this is either 1 or 0, they are different. If they are the same, we are switching that one off. So this is 0, this is again 0, 0, and 1. And not is basically just swapping those. So if you have just some value like this, if you're using the not operator, it's gonna be the opposite. So all 1s become 0, 0 become 1, and so on. So why do we need this? Lots of operations will be done with this, especially something called bit masking. So if we have a number like this, let's do another binary number, just some random one again, probably doing the same every time, but anyways. If we're doing some operations here, for example, this is a matrix, or this is the result of some scalar value we're doing in our data set, sometimes we will need to do some kind of masking in order to do some operations. For example, if you don't want to touch any of these bits in here and just want to do an operation here, the masking will look something like that. This will be 0, 0, 0, and only when you have ones, you can do some operation. So for example, if we do an AND operator here, the result of this will be, again, remember, only when these are 1, when they're both 1, you will do some operation, right? So the result of this will be 0, 0, 0, 1, 0, 1, 0. As you can see with these values, it's basically just masking it and then you're just doing some operations in this remainder one. Really important. Also, we can check a concept called bit shifting. If we have a number like this, 0, 0, or let's do some actual number. Let's do 20. Again, based on our chart so we don't forget, let's have it here. Someplace, I'll just do it here on the top. 1, 2, 4, 8, 16, 32, 64, and so on. So 20 in binary will be 1, 0, 1, 0, 0, right? So let's have the number 20, which is OB10100. If we're doing bit shifting to the left, which will be this symbol, we can specify how many bits are we shifting. So let's shift 20 by 1. What's gonna happen is every number, we're gonna move it to the left. Therefore, it will be the same, but with one number at the right. Obviously, this became another number. And now let's deconstruct this to check which number is this one in binary by doing bit shifting. So I will start with the same graph as up here. 1, 2, 4, 8, 16, 32, 64. Now we have a number here. If you add 32 plus 8, it will be 40. And we have zeros for the rest. Take a look at what happened here. Our original number was 20. By doing bit shifting of 1 to the left, we double this number. So we actually multiply 20 times 2. And this is what's happening in your machine when you're doing mathematical operations. Multiplications, divisions, when you're adding numbers, you're doing bit shifting to the left or to the right. So if you do an exercise by yourself and you do bit shifting of 20 and you shift it by 2 to the right, the result will be 10. So you are dividing it by 2. Really important to know, the closer you go into your hardware, the better operations you can perform and the better development you can do in general. We will see more about bitwise operations as we go, especially when we're dealing with arrays and trying to find out some commonality in between two sets of operations, two sets of vectors and things like that. And we'll probably use bit masking in some places as well. So just for you to be aware, this is how the architecture is behaving in the backend.